Uh, okay, hopefully the stream should be fine. Okay, I think it's on. We had trouble last time we did this. Don't know what happened last time, but it looks okay now. So yeah, hopefully it should be okay. So today we're doing GCSE with math revision again. For paper two, which is next Wednesday, I believe, on the morning. So yeah, that's the aim of this stream. And so what I've done is, well, I've looked at paper one, and I've also looked at other paper twos and threes, the calculator papers in previous years, and I've compiled the most likely questions that have come up, right? The questions, the topics that are going to be of most use to practice, in my opinion. However, I will say from the get go, you may have to make sure you learn and revise everything. Um, and just as though there is no actual concrete way to predict entirely everything on the paper. All I've done here is, yeah, the predicted topics, the topics that are most likely to come up based on what I've seen on the paper that you've just done and what is usually on the paper. But obviously, you can't rule anything out, and so from the get go, I'm just going to say don't use this or any sort of predictions or videos or revision um, as your only source of revision. You need to make sure you sorry, you need to make sure you practice everything, especially if you're aiming for those top grades. Yeah. But with that said, this will still be of great use, right? To practice the stuff that has a high chance of coming up, right? So you can get loads of marks. And so I've compiled about 80 marks worth of questions, and it pretty much would resemble a paper. The difficulty scales, I believe, in the way of a paper does, right? We have some nicer questions to start off with, and then it goes towards the very end to like the grade nine sort of question. So it'd be of use to anyone. And although it says higher, these first few questions will be on the top end of a foundation paper, which I think most people probably struggle with. Right at the end of the question of the paper, those sort of questions. So this first bit anyway, will be of use to everyone. But this is mainly aimed at higher. Let me know. I don't know. If someone wants a foundation one, let me know. But I haven't looked too much into that, if I'm honest. But if there's a huge demand, though, I can sort some out maybe. But anyway, that's the aim today, just to go over these questions. And yeah, I guess I'll stop waffling. So, and also to say before we jump in, every question, uh, I've underlined it there badly. But you can see the paper it came from if you ever want to look at the mark scheme or whatever, see where the question came from. And the marks for the question in total are also there. Okay, hang on, I need to check the chat as well. Because sometimes I've been missing chats, which I do apologise for. Uh, but yeah, anyway, so the first question then, I'll just say for actually the final thing before we start. I'll just say how we use this is perhaps the best way to get use of it is well to pause the question yourself, especially questions that you're a bit iffy on, and then try and work through it yourself first, and then we'll work through it together right afterwards. So you'll see what you're meant to do and how to approach the question. Or if you're more confident, then you should be able to think, oh, you do this first, and then you can do this, you can do this, and you can kind of see where I'm going with it. And if you get to if you get the right answer and the right steps, and you're quite confident in it, yeah. So it's good for recapping. Anyway, so with that all that said, let's do the first question. And this is a very, very, very typical like calculator question. It's just asking you to use your calculator essentially. It's testing you how it's testing if you know how to use a calculator. So this is a very common sort of question. So question one, start the paper. Work out this value here and write down all the numbers in your calculator. So, well, essentially, just put that nasty fraction into the calculator. which I've got here. So, what we're going to do. So, first of all, you're going to want to do a fraction, which will be this button here. Then you want to do 25, then minus the square root of 43.87. Then go to the denominator. So then that'd be 6. Add 2.1 squared here. And then essentially equals, right? And you get this number here. So all the figures in your calculator display, you just copy the number down, right? So 1.76, what was it? 527, 923. Cool. And that's for 2 marks. 2 marks implies a method mark, but I think you'll just get 2 marks for writing the right answer down, perhaps. I'm not sure what you'd write down. But anyway, that's that. And then for part B, said write down the reciprocal of 0.625, where you should know that the reciprocal, as a definition, just means 1 over that number. So 1 over 625, 0.625 is the reciprocal, and then you put that into the calculator. So 1 divided by 0.625, and you get 8 over 5 or 1.6. And that's going to be your answer for 1 mark. Cool, so for that you just need to know what the reciprocal means. And that is 1.6. Cool. Also, let me know. I'm trying out a different software to what I usually do. So let me know this is better than the other way I display it. I don't know. I like it so far, but let me know. Okay, we're on question 2 now. So we have a right angled triangle, and we're given some information about the lengths, and it says to work out this length x here. Well, actually, it's a right angled triangle. So with right angled triangles, you're either going to need to use trig or Pythagoras. But actually, we know nothing about the angles. We're not asked about the angles. So we're asked about the sides, so it's going to be Pythagoras. And actually, I believe it's in the formula sheet, but you should really remember it by now. That the opposite and the adjacent side is the squares of those. So a squared plus b squared is c squared. The squares added gives you the hypotenuse squared. So if we label, doesn't matter which way, but if we label, say this is A and B, and then the hypotenuse is C, then if you square both sides and add them, you get the hypotenuse squared, and that would be your formula book. So let's write this down then. So the first length is 4, so that's going to be 4 squared, and then missing angle B is going to be angle. Big missing side is x, so that's x squared, because we got square everything, of course. And then the hypotenuse squared is 8.5 squared. Just to say, let's work that out on the calculator. 8.5 squared is 72.25. Okay. But we want to find x. Actually, we can let's work this out a bit more. Actually, so 4 squared, we can simplify 16. Add x squared is 72.25. So we need to solve for x. That means we need to rearrange. So x is on its own. So how do we solve? Well, we just subtract 16 to both sides to get x on its own. So therefore, x squared is 72.25 minus 16, which is 56.25. But that's x squared. To get x, you're then going to square root it, right? So the square root of 56.25 is your x. And that is going to be 7.5 centimeters. Just a final note with that. You do not do plus or minus, because if you have minus for x, you have a negative length. You can't have negative lengths. So you just you ignore plus or minus. You just take the positive in this case, okay? So make sure when you are solving for stuff like this, make sure you consider the context. So if it's anything to do with time or length or anything like that, you're going to need the positive, okay? But yeah, that's that question. Cool. Hang on. I might turn down the thickness of this a little bit, actually. Okay, let's try that. Okay, cool. Okay, so that's question 2. That's with Pythagoras. So if you see a right angle triangle, you should be thinking either we do trigonometry or Pythagoras, depending on what you want to work out and what you're given. Here we are just given both sides, and we need to deal with sides. So it's given Pythagoras. Trig is when you deal with angles. Okay. But yeah, that's just a Pythagoras one with a little solving of equations. Cool. Question 3. Again, this is also a very, very common question. I think this has come up on every single exam series that I've noticed. It's just a 1-2 marker, usually. But it's just something it's best to do, right, to pick up the marks. So this is about error intervals. So we're given the number D, rounded to one decimal place, it's 12.7. Then it says give the error interval. Usually they are nice enough to give you the interval, but they don't have to. But just know it's always this side round. I'll explain more in a second. But the error interval. So what is the error interval? I'm not the biggest fan of this sort of wording. If I'd prefer to call it the bounds for D, or the possible values of D. It's like I don't know, the error interval. I don't know. It's not the best terminology to explain it, in my opinion. But it just means like the bounds of D, so the range of values. And so, what are the range of values? Well, because it's rounded, there are a certain amount of certain possibilities for D. Well, 12.7. Then we just need to see what the highest and the lowest possible value. So if we have 12.7. The height. Let me get rid of -16. So we need to think of the lowest number that will round up to 12.7. Well, it's one decimal place, so it's going to be. If you think about it, if you round up a number, it has to be 5 or higher. So we need to consider the half of this. So it's minus 0.5, 0.5, isn't it? So then 12.7 minus 0.05 should be 12.65, right? And that will be your upper bound, right? The lower bound, because any number above 12.65, that 6 will round up to a 7, because it's at 5 here. So we need to consider if the next number is 5 or not, essentially, which comes from this 0.05. And any number higher than this will round up to 12.7, because obviously 5 is the smallest digit that makes you round up. If it was 12.64, that would round down to 12.6, because obviously 4 is smaller than 12.7. So yeah, that's the lowest number. Now the highest number, again, you're going to add by the same amount. So 0.05 of 12.75. Again, because the only digits are 5, round up or down, right, depending. But here, this, however, is a bit of a different story. This is actually, if you think about it, this number would round up to 12.8, So that's 12.8. However, that is the upper limit because really, if you think about it, the actual biggest number that would round down to 12.7. So again, think of it as the number line if you wish. The lowest number is 12.65, 12.7 is in the middle, and then 12.75 is at the end, right? Every number in between would round to 12.7, right? That's the whole idea. This branching is what is going on here. But 12.75 itself does actually rounds up to 12.8. But think about what would be the highest number that would round that's still round down. It look 12.744444. You know what I mean? It's all I guess technically 7.4999. That'd be like the next number down, right? 12.75. The next number down is 7499999 and so on. But this number goes on forever, right? We cannot physically write this number down, really. We could perhaps say 12.749 recurring, but it's not a physical number we can write, you know what I mean, write down. Whereas this is just point blank 12.75. But this is ongoing. There is no cut off point really. Um that we can write down physically, right? It goes on forever. So the highest number actually just goes on forever. It's like infinity. So what we do instead is so actually we consider the next number, which we can write down, but we say any number before this does round down, but the number itself doesn't. That is why here the upper bound of 12.75, and this is going to be 12.65, it cannot be 12.75. That's why there's a strict inequality here. But we say any number less than this, like this number here, no matter how many nines we have, that will all round down to 12.7. But that's the upper bound, okay. But for the lower bound, we can include 6.5 because that's the lowest number. But the number before 7.65 12.65 would be 12.64999. Again, similar. But this will round down to 12.6, wouldn't it? Not 12.7. So that is the first number, 12.65, that will round to 12.7. And obviously that's the upper bound as well. Let me get rid of this now, it's a bit messy. Let me write it down here, 12.65. So if we so these are the bounds, right? So essentially, you just got to write down the bounds using how much you rounded to. And yeah, that's essentially the sort of process behind that. Again, it's just one mark, but essentially, when this question comes up, it's just asking you to write the lower bound and the upper bound of the number. And it comes from think about the highest number that will round down to 12.7 and the lowest number that will round up to 12.7. And that's the sort of methodology. But yeah, okay, not to confuse you too much, hopefully, but that is what's going on here. But yeah, anyway, so that's like question 3. Let's go down. Question 4, Venn diagram one. Nice. Okay. So with Venn diagrams, essentially, you consider usually 2 or 3 events, right? So here, event A, or list of A, or set of A, is the set or the list of even numbers, and B is the list of factors of 10. We put all these numbers in the chart in the circle, right? And what happens is there we consider these 2 lists or events or whatever, and if a number or anything doesn't belong to these, so if we have a number that isn't even or a factor of 10, then any other number goes outside the box. Well, not outside the box, outside the circle, but inside the box here. Okay, but every single number that we can think of has to be in the box, in the rectangle. Because what this weird sign here is, that little, I don't know what it is, I don't know what it is. This really weird symbol, that is the universal set. So that's universal meaning everything. So every possible number that we consider here. So these are the numbers we've got to work with, 1 to 10. It has to be in the box. Because you can either think about it, for these 10 numbers, it's either an even number, a factor of 10, or both, or neither. Okay, so these are everything in the box is encompasses every single possibility here. Um, and that's really all what you need to know. So let's put the numbers in where they belong then. So um, again, we've got these numbers to work with, 1 to 10. But the best way to approach this is really to work out what belongs in A and B. So A is an even number. Well, the even numbers are going to be 2, 4, 6, 8, and 10, and that's going to belong into the circle A. However, we do not just put them all in A, because this overlap here means that numbers can be A and B. The even numbers can also be a factor of 10. So we need to consider the numbers that go in the overlap. And then we work from there. So the best way to do that then is then think about B as well. So what goes into B? So factors of 10. Well, what are the factors of 10? Well, it's going to be 10 in itself, 2 and 5. 3 doesn't go to 10, 4 doesn't go to 10. So these are your 4 factors. So that means 10, 1, 2, and 5 are in B, right? These 4 numbers. Now, which numbers, the best way with these Venn diagram questions is to work out what goes in the middle, then work your way out the circles. So what goes in the middle? Well, to work out what goes in the middle, so what numbers are in both lists or in both sets? What numbers are common in both? Well, 10 I notice is in both, so you can put a 10 inside here. 2's in both, and that's it really. 5 isn't in A, so that's it. So then the rest of the numbers go in this bit outside the overlap. So it's going to be 4, 6, and 8. And B is just 5. Okay, cool. But I did say everything else has to be outside the circles in the box. So what other numbers are missing? Well, remember our list was. Did I write the list down somewhere? I'll write it down again. 1, 2, 3. Well, we don't need to because the list is here actually. Uh, the list here. Well, 1. Uh, oh, 1's in there, so I didn't see that as a 1 here. 1 is in B as well, but not in A. Okay, well, we already wrote 1 down. We wrote 2 down, but we didn't write 3 down, so 3 has to be outside somewhere because it's not either. 3 is not an even number or a factor of 10. Okay, then what about 4? 4's in A, so no. 5's in B. 6 is in A. 7's in neither, so 7 has to again be outside. 8 is in A. 9 is in neither, so 9 can be written somewhere else, say here. And then 10's in there as well. And you should know if you've done it right, because there should be 10 numbers in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we filled in the Venn diagram correctly then, hopefully. Cool. So that is part A. So the best strategy again is to work out what numbers belong in each set, and then you fill in the middle part, and then you work your way out. Okay, that's the best way. Okay. Then we're given a number is chosen at random from the universal set. So this set here, so the set of all the numbers we have. So from 1 to 10, we pick a number. Find the probability that the number is in the set A intersection B, or A and B. So this symbol here, that means and. The way I like to think of it is this looks like an N almost, like a lowercase n. and and makes the n sound like and. So like you can think of and. Um, I don't know. That's the way I think of it. Really, the sound it makes and n. I don't know. So because it's and, that means it has to belong in A and B. Well, what numbers are in A and B? Well, 10 and 2. But that's two numbers out of 10. Because remember, probability is the amount of things we want, which are two numbers, over the total, which is 10, because we're out of 10 numbers here. So that is your probability. So what we want is the numbers in A and B, which is two of them, and this is the total. So that's our probability. 2 over 10. We don't need to simplify that. It doesn't ask us to. So I can just leave it as 2 over 10. Okay, so let me just talk a bit more about this then. So this is and. Again, I like to remember because it's at the end sound. U, which is this little shape here, means the union, or we really just say or, essentially. So if you had A or B, we'd represent it like this. And that's the numbers that are in the circles A or B. So that would be your 4, your 6, your 8, your 10, your 2, your 5, and your 1, for instance. Not for done here. 4, 6, 8. Okay. Um, and that means or. Uh, again, this might be a bit more of a stretch, but I guess the U makes a little O sound. I don't know. Or like you. I don't know. That's how my brain thinks. But there's a distinctive N sound with and n. You know what I mean? But U is a bit more. I guess a bit more of a stretch, but you should know it's either and or. So if you're getting confused, you should know and is n. It's this little N shape, because it sounds like an N, I guess. And then U would be or. And you also need to know about this apostrophe, which means not. For example, we could say a dash. That would mean not in A. So all the numbers that are not in the circle A, that would be your 5, your 1, and the numbers outside as well, 3, 7, and 9. So those are the three things you need to be aware of. But that's how I like to remember and anyway. Obviously, there's other mnemonics ways of remembering. Obviously, feel free to comment. But I don't know. For me, that's how I like to remember anyway. Okay. So that should be fine, hopefully. Okay, we're on question 5 now. Um, Again, this is kind of like a simplish like ratio question that can come up. I've noticed it on a few papers, so I left to cover it. So we are told it takes 14 hours for 5 identical pumps to fill a water tank. How many would it take for 4 pumps to fill the same sort of water tank? Okay, so it, 5 pumps takes 14 hours, but think about it. You fill You kind of want to find the time it takes to buy it for one pump. So one pump, if you think about it, well, 14 hours for 5. If you need to fill the same amount of water, it's going to take longer for if you only have one pump, right? One pump has to do the same amount of work as 5. So therefore, it's going to take 5 times the amount of time. So it's going to be 5 times 14, which is going to be um, 70 hours. Okay, so hopefully it makes sense. So if you're decreasing the resources you have, so say if you have less pumps and you got to fill the same amount of water in, it's going to take longer, isn't it? And that's the time for one pump, and that's the strategy for these type of questions. If you have multiple things, find out what one of those things is worth, and then you could scale it. Because now what we could say is, well, one pump takes 70 hours. Well, 4 pumps is going to, in the same amount of work, it's going to divide by 4. It's going to take 4. It's going to be 4 times quicker, right? So 70 divide by 4 to share the workload now between 4. That's going to be uh, uh, oh, uh, 17.5. Okay. So I think that makes sense. I guess a common pitfall people might fall into is you'd think you probably use ratios, right? So you probably say like 14 is like in the form 14 to 5 or something like that. And then you divide down to say, well, divide by 5. 14 over 5 is the time it takes for one pump. But actually, think about it in this context. The less resources you have, so the less pumps to do the same amount of work, it's going to take longer. So instead you have to times because it's going to take longer if you have one pump than 5. Because essentially what he's saying is 5 if you have 5 pumps, yes, doing the same amount of work, 5 pumps here, and that does and in total that does 14. No, sorry. Well, we know no, we know the total amount of work that has to be done is 70, right? That's 70 hours of pumping, but that's split between 5 of them, and each of these 5 takes 14 hours, right? So 14, 14, 14, 14, 14. So then to find the total amount of work, the total amount of hours, you add them all together, right, to get 70. But if there's only one pump, then that pump here has to do all of this work by itself. So that means one pump is the total 70, which is what we've done here. So then to work out how many times 4 pumps takes, then you have to divide by 4, right? To then redistribute it. To do this to do 70 hours of work between 4 pumps. Hopefully that is clear. Okay, it's fairly simple to marker, but I think that's an important thing to go over. Okay. Um. Okay. We're on question 6 now. We're flying through this actually. Um. So question 6. So it's a speed, distance, time question. So immediately I'm thinking of this formula here, this little triangle of distance, speed, and time. That's what I'm immediately thinking of. So remember, it goes like that. So distance, if you want to do distance, you'd cover it up and say, well, you do speed times time. Likewise, if you wanted speed, you'd cover that up and say distance over time. This bar here means a fraction, or we're dividing by, yeah? Likewise, time, cover that up, then you do distance divided by speed. Anyway, that should be in the back of your mind when you see this sort of question. Um, but yeah, so let's read it. So Ollie drove 56 kilometres from Liverpool to Manchester. He then drove 61 kilometres from Manchester to Sheffield. His average speed from Liverpool to Manchester was 70, and he took 75 minutes to drive from Manchester to Sheffield. Work out his average speed from his total drive from Liverpool to Sheffield. Okay, so what's happening here is you need to split this into 2 parts, right? There's 2 parts to the journey. You got Liverpool to Manchester, and then you've got Manchester to Sheffield, right? And overall, you're going to have Liverpool to Sheffield, right? And that's the total drive. Okay, so we have to work this out bit by bit. So what do we know? It's distance, speed, and time. We're going to need to know that bit. So the distance from Liverpool to Manchester, we are given is 56 kilometres. At the speed, we're given actually to 70 kilometers per hour. So therefore the time, well, the time, we do not know, but we can work that out. Because if we cover this out, like I said, use this formula, it'd be distance divided by speed, right? So that's distance over speed. That's going to be 56 over 70. And if we work that out, that will be 0.8 hours, right? Be careful the units, it's in hours. Okay. Then we need to work on the second part of the journey. So we are given distance. Are we given distance? Yes, we are at 61. kilometers. We are given the speed, which is, we aren't given the speed. And then time, we are given 75 minutes. Well, actually, everything's in kilometers per hour, isn't it? So we need to convert minutes into hours here. So really, 75 minutes. You could probably spot it's actually one and a quarter hours, right? But if you weren't sure, well, you should know that 60 mins is 1 hour. So then to get to 75 mins, what are we timesing by to get 60 to 75? Well, you could do 75 divided by 60 to work that out. And your multiplier is 5/4, which is 1.25. That's what you're going to times by. And so therefore you're going to do the same here. So the 1 times 1.25 is 1.25 hours. Okay. So your speed. Well, actually, do we need the speed? I don't think we do need the speed actually, because if we want to find the speed from Liverpool to Sheffield, all we need is when you find the average speed over a journey, you just need the total distance and the total time. Well, the distance and the time we add together. Because if you travel 56 kilometers and then another 61, then the total distance is 56 add 61, which is 117, right? And that being kilometers. And likewise, the time, if you go from one part to another, the total time is just adding them together, right? So the time, well, we've already seen is 0.8 hours for the first part, and then 1.25 hours in the second part. So combining the two parts together, like with the distance, you add the time together, so 0.8. 0.8 add 1.25 is 2.05 hours, right? And that is also why it's important to convert the units here from minutes to hours, because if you add in the same time together, you can only add them when they're in the same units. Okay, so that's the idea. So we've got the total distance and the total speed. So the total time. So the total speed is going to be total distance over time. So therefore, the speed or the average, and it's an average because you're really just assuming you're just breaking up one by one. Anyway, so the average speed. So that's the total distance over total time. So that's d over t, remember. That's going to be 117 to divide by 2.05. And then you put that into the calculator. 117 divided by 2.05. You're going to get this really weird number here. 57.07 to do decimal places. And that's kilometers per hour to 2 dp. And that's your average speed for the total journey. Put that here. Okay. So yes, that's the strategy with these type of questions. If you are given two parts and then you want to work at the total or the average speed, you need to consider what the say if you have a road here, for example. I'm going to get rid of this little thing now. Say if we had this journey here, we start here and then again we end here. Say the first part is here and then the second part is here. But the distance, you're just going to add them together, right? That would make sense. The total distance is just the two combined. Same with the total time. If I take half an hour and then another hour, for example, then overall it's going to be an hour and a half. You know, we can just add them together. The speed, however, does not work like that. We cannot just add them together. Okay, speed doesn't work like that, but the distance and the time does. And I guess if you think real logically in real life, that does make sense, right? There's distances and time add together like that, but speed doesn't. Okay, hopefully that made sense. That's the sort of methodology with these, and if for the same with density, mass and volume. So if you have a mass and the volume of like two different parts, you have you can't just add the densities together. And you're going to see that there's another question with density later on, actually. So we'll see it there as well. But with density, like with speed, you cannot just add the densities together, but you can add the mass and the volume together. So then the total density would be the total volume mass over the total volume, according to this formula here. This little triangle MDV, which you should be familiar with. Exactly same concept with speed. You need the total time and the total distance, so then you can work out the total or the average speed. Cool. Okay. Hopefully it made sense. And therefore, because of that, we didn't need to work out the speed here because that's useless, really. Because we can't use the individual speeds in our final answer. We just need the time and the distance. That's all we needed here. So yeah, hopefully that is clear. Okay. Okay, now we are told he drives from Barnsley to York, so it's a different thing now. His average speed was 80, and then 60 for the two different parts of the journey. He said that the average speed can be found of the overall journey can be found by working out the mean of the two of them. If he's correct, does that tell you about the two parts of his journey? Okay, so average speed is what I'm picking up here. So so he said it's found by working out the mean. Let's let's play around with that actually. So the mean of speed, well, you're going to add the two speeds together, then divide by two, aren't we? It's going to be 80 plus 60 over 2. Um, and what would that be? 70, right? Um, okay. But the only way that can happen, if you think about it, 70 is between 80 and 60. The only way that can happen is you can split the two parts of the journeys equally, isn't it? Because then if you're dividing by two, we're splitting in the middle, aren't we? So the only way that the mean speed will work out like this, we can just divide by the individual speeds, which means if we're dividing by two, we're basically finding the midpoint, aren't we, of the two individual speeds. So if the total speed work was 70, so it was the mean. Well, if we divide it by two, like I said, it's in the middle, right? So that would mean the journeys would have to be equally split apart, equally distance. Um, um, yeah. Oh, and it'll take the same time. So actually, what does that tell you? And for that to happen, has to have the same time because the distance is halved. No, not distance, but the journeys are halved, right? Half the time, and I'll show you a more mathematical thing in a minute. So the because of this, because it's basically at the midpoint here, because we divided by two, that means the journeys, or the two journeys, have to be done in the same time. Because it's the same time, then obviously they're equal, right? Which means we can split by two. Then the other way to think about this, which is a bit more technical, we can actually express the speeds in terms of the first. So say dot speed. This is speed one, S1, and speed two, which corresponds to the first and second parts of the journey. Well, that's the first distance over the first time. add second distance over the second time over 2. Um, and so then, um, but for this to happen, if it's 17 in the middle, the times have to be the same, really, don't they? That would mean if T1 is equal to T2, well, you're just adding D1 plus D2 over T1, for example. If T1 is equal to T2, that's the same time. So you could just add the times, like when you add with fractions, you with the common denominator, you just add the distances. But that's all over 2. But if you're dividing that by 2, we can just say that's 2t. Um, and therefore 2t, that's telling you it's 2 lots of the journeys, 2 lots of the time. But if each journey is the same time, then the time of the total journey is 2 lots of t. So the only way, essentially, that the mean will work out like that is if we can add the fractions like this. And the only way we can add the fractions together like this is if the time is equal on both. And so therefore, the time of the two journeys have to be the same if the average speed is the mean of the two components, right? Okay, that's probably a bit confusing, but I guess, a more mathematical way of looking at it. But it's the time, right? The journeys have to be the same time, so therefore that would allow the mean speed to, or the average speed to be split up like this, right? And then we can split this up over 2, which suggests that the two journeys are in the same sort of time, right? Um, okay. Yeah, it's a really awkward one, Marker, to be fair. But yeah, hopefully, I guess the best way to think of this, again, just to reiterate, is the fact this is a midpoint, right? You're divided by 2. You do not the midpoint. You in the in between. So what's in between in the middle? Well, if it's in the middle, then that means the two journeys have to be the same. So for that to happen, the time has to be the same. Obviously, you can do more distance in one journey than the other, but it has to take the same amount of time. So then we can split it into 2 parts. Okay. Okay, let's get rid of that awful question. Now we're on question 7, and we're on box plots. So, the box plot shows information about the sales of an online store, and we're given the box plot here, and it says 3/4 of the given data lies between 160,000 and 350,000 because these are the values of the lower and upper quartile and is wrong. Explain why. Okay. So what this is saying is 75% of data lies in the essentially the interquartile range, isn't it? The interquartile range, remember, is the upper quartile minus the lower quartile. So if it lies between the upper and the lower quartile, it will be in this range here. But actually, it's only 50%, isn't it? Because we know the lower quartile is the bottom 25%. So that's going to be 25% here between the minimum and then the lower quartile. Likewise, the maximum is the upper 25%. So that's going to be between the upper quartile to the maximum. That's another 25%. So really, the interquartile range only encompasses half the data, not 75%. So that is why it's wrong because the uh, the data. No, what should I say? The values between the upper quartile and lower quartile uh, are only between 50% or half of the data, not 75%. Okay, so he's got his numbers mixed up there. So it's 75%. So it's 50% up, not 75%. Because of the fact that the distance between the minimum and the lower quartile is 25%. Likewise, the upper quartile to the maximum, there's another 25. Um, so yeah, and also the distance between the upper lower quartile and the median is 25. Um, and yeah, that's essentially the reason behind that. Um, yeah, hopefully it made sense. But we'll move on. Um, Cool. So then we're given some data, more data about sales in a shop. So the last one was about online sales. Now we're talking about in the shop. And so we need to draw a box plot. Okay, well we're given all the values for us, which is quite nice. Now, but these box plots, essentially, obviously, you need to plot the minimum, the low quartile, and so on. You need to know what each box is worth. Well, actually, if you see here, there's 10 squares or 10 boxes between 0 and 100. So each square or one box is going to be worth 10 units, right? So here, if it's 30, well, the minimum is going to be here, right? No, not there. It's going to be really hard to draw. It's going to be there, right? Because then this will be 50. So then two boxes to the left is going to be 30. So then if I draw it like that, that'd be the minimum, roughly. Uh, hang on, let's do that again. Okay, roughly there. So we need to plot the minimum first. Then we plot the low or lower quartile. That'd be 80. So that's going to be here, right? 80. Two away from 100 to the on the left. So like that. Then you draw the line that connects them, like that. Um, Obviously do this with a ruler, but obviously I'm just doing a bit freehand. But yeah, okay, then we need to plot the median. That's going to be 170. Well, that's going to be here, right? Because obviously that would be 170 there. Two box. Oh, hang on, that's one. No, that's two boxes in. Oh, okay. But this time you have to draw a box like this. Then we need to plot the upper quartile. That's going to be 260. That's going to be here. So that's going to be this line here, right? So let's go there. So again, you draw the line that connects them. Then we need to draw the maximum value, right, which is 350. Okay, but that one's quite nice. It's in this main part here, right, the main box, and that's gonna be 350. Then therefore, and we need to draw another line. Now we don't connect to draw the box like that, and that's it. And if you was stuck, they give you another box plot, so it should have the same sort of shape as this, which it does, right? Okay, so that's the box plot, right? So you just need to know to plot your values and what a box plot looks like. The biggest thing to remember with box plots like this, they seem to be the same sort of thing every time. But the main bit is you need to know what your scale is, right? How much each box is worth, and then you can use that to plot it. Okay. But yeah, fairly typical box plot question. But yeah, now we're on part C. So then part C says compare the distribution of the sales of the online stores with the distribution in the shop. Well, as I've said, these two box plots represent the online store sales and the shop sales. So we need to compare them. Well, there's two things you need to remember when you're comparing them. When you compare two box plots, you uh, you can you can compare the average because the average is the median value, right? The median, and you can compare the spread. Now, the spread tells you how far away the data is away from the mean. So, say if you have data that's really clustered together like this, it has a low spread. But if it's more scattered, let's get round this, more scattered from each other, then it has a higher spread, a higher variance. Okay, so more data is away from the median, right? Or I guess the range, if you think of it like that. But the spread is the IQR, interquartile range, which is the upper quartile minus your lower quartile. Now that one you're gonna have to do some maths in. The median we can spot right away. It's the middle line here. But the IQR we're gonna need to do a bit of maths. So let's comment on the average, right? So which one has a higher median? Well, the median here is 170. Um, but the median on here in the upper box plot, that's 200, right? So the median is 270. Oh, no, 200. 270. Where we go? 200. So the online store sales have a higher average, right? So online store sales are on average higher than in the shop. As this online median or the online store median is higher. And you could say that's because 200 is greater than 170, right? So the median of the online one, of which is 200, is higher than the in the store, which is 170, which is here, right? So then that's one thing we need to comment on. Notice it's 2 marks. We need to comment on the spread. Well, the spread, again, we have to work that out. So it's the IQR. Now, the IQR for this one, let's get rid of this now. So the interquartile range, like I said, is the upper quartile, 260, minus 80, which is going to be 180. And this one, the IQR, uh, well, what's the upper quartile? It's 350 right here. And then the lower quartile is 160. So minus 160, you get 350 minus 160. You get 190. So again, the uh, um, the interquartile range in the online store is higher than in the shop because 190 compared to 180, right? So the online store again, all the online store sales has more spread than in in the shop. as it has a higher IQR. And I believe you can just abbreviate it like this. The examiners will know stuff like this. It's a common abbreviation, right? IQR, especially in this context. They'd be looking out for stuff like UQ for upper quartile IQR, LQ for lower quartile, and so on. But it has a high IQR, and you can say because 190 again is bigger than 180. So that's the IQR of the online store, and that one's the IQR of the in the shop that we worked out. Yeah, cool. Okay, so that's it for 2 marks. So again, with these box plot questions, you should always be thinking about the median for the average and the spread, which is the IQR. And for 2 marks, you should always be commenting on those two things. Okay. Okay, we're question 8 now. So we'll give a lava flow from a volcano at a constant rate of 11.9 meters cubed per second. Work out how many days it takes for that amount of lava, a very big amount of lava, to flow out from the volcano. Okay, so the critical thing here is to work out that this is all about rate and meters cubed per second. So that's telling you that 11.9 meters cubed every second leaves the volcano of lava, right? So then, to work out how many to get to that amount of volume, 67 million, well, we're going to need to scale it to 67, and that's equals 1 second, I guess. So 67 and 205 and 600, that's going to be some lot of seconds, right? How do we work that out? Well, how do you get from 11.9 to 67 million? Well, you're going to do 67 million, 205,600 divided by 11.9, and that will get you put that into the calculator. 11.9. You get this awful number here. 5, 6. What was it? 5647. 529.412. Okay. So that's how much we times them by. But 1 times this amount is going to be this amount. So it's going to be this amount of seconds, right? Okay. But so that's how long it takes for that amount of lava to flow in seconds. But it wants it in days. So we're going to have to use some conversion here. So you're extremely unlikely to remember the conversion from days to seconds exactly. But we can work this out because you should know that, well, 1 day is going to be 24 hours, right? So then that's also equal to, well, 24 times 60 minutes because there are 60 minutes every hour. Let's work that out. Um, so 24 times 60, that's 1,440 minutes. So that's how many minutes are in a day. But then we can then times this by another 60 to get seconds. Because again, there are 60 seconds in a minute. And then we work that out in the calculator, times by another 60. You get this number here. 8 6 86,400 seconds. So that's how many seconds are in a day. But we want this amount of seconds, don't we? 5 million or so seconds. We need to convert that into a day. Well, how are we going to do that? Well, let's rub this out here. You're going to divide, right? So if one day is this amount of seconds, well, then to get to this amount of seconds, 5 million, you're going to divide by the 86, right? So 5647, 529.412, that horrible number, divided by 86400. That'll tell me how many days that is worth. So let's work that out. 5647, 529.412 divided by 86400. You're going to get this 65.336 blah 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 blah, right? Days. Okay. Now that's how many of that lava leaves the volcano in days. We just need to round it to the nearest day, so the nearest whole number. So that's going to be 65 to the nearest day. Okay. Not surprisingly, a bit tricky. The numbers are really awkward to work with, and this horrible conversion you have to do here from days to seconds. Uh, but yeah, that if you have unknown conversions like this, try and convert it to stuff you do know, and then eventually you get the conversion you want, right? So you should know one day, 24 hours, and you should know how many hours in minutes are in an hour, and how many seconds are in a minute, and then you can work it out like this. Okay. Cool. Hopefully it made sense. But it's simple ratios and scaling, right? But it's just a bit, the numbers are awkward, so it can be quite hard to visualize. But hopefully that made sense. Okay. On question 9 now. So the first part is just an index law question. So we need to express this as the power 10. So we need to make this look like 10 to the n, right? Some number n. So this whole thing needs to simplify to this. But we're going to use our power laws, aren't we? So root of 10 to the 360 over 10 to the 150 times 10 to the 90. Well, the best way for this, I think, is to work inside the fraction first and work our way out. There are multiple ways you can approach this, multiple steps you can take. But I think the best way is actually simplify it bit by bit, in the sense that I think it's best to start the denominator there, because the denominator is the first thing I can spot we can work with. Because I think we can add these powers together. So 10 to 150 times 10 to the 90. Well, you're going to just add them, aren't we? 10 to 150, add 90, because you should remember the power law. A to the m times a to the n, you just add them, okay? That's the power law we're using here. And that will just be 10 to the 240, okay? Cool. So now this whole fraction then simplifies to 10 to the 360 over 10 to the 240. Now I can work out the fit inside the fraction, right? I can do the fraction because I should know the power law also. A to the m divided by a to the n is now a, you subtract the powers, m minus n. So that then that's going to be 10 to the 360 divided by 10 to the 240. That's going to be 10 to the 360 minus 240. So that's going to be 10 to the 120. So then this whole thing becomes root, and then that's the division here, 10 to the 120. So now we just need to work out this square root. Okay. How are we going to approach that? Well, you should, if you're converting everything into powers, we can convert the square root into a power, can't we? Because you should remember that square root is the same as raising it to the other half. Okay. So this is going to be 10 to the 120, all raised to a half. Well, then you're going to need to power the index law, a to the m, all raised in a bracket by another power n. You just times the two powers. So that's going to be 10 to the 120, or 120, times by a half. So a half 120 is 10 to the 60. And that is your power of 10 at the end. Okay. So that's a power laws question. So we given part B. So it says Liam was asked to express 12 to the 50 squared as a power of 12. Liam wrote 12 to the 50 squared is 10 to the 50 squared, which is 10 to the 200. So he worked out 50 squared here, and he's wrong. Well, he's wrong because you don't square 50. You don't raise 50 to the 2. You times by 2. So I'd say 12 to the 50 to the 2 is 12 to the 50 times 2 equals 12 to the 100, not 12 to the 50 squared. Okay, because that is, again, that's the same part as the index law we just used. A to the m to the n, you're timesing the powers. You're not saying n to the power n. So, for example, if we have this squared, that is not the same as saying a to the m squared. You're doing m times 2, not raising it to the power 2. Okay. Okay, just one mark there. No need to overcomplicate too much, but that's the sort of thing, right? That's the correction to the mistake that Liam made. Hopefully it made sense. So just he misused the power law there. That's the wrong one. Okay. Um, question 10 now. Also, I do predict as well that's a very, very likely topic to come up. I was really quite surprised to see there wasn't an index law question in the non-calculator paper, because obviously, in theory, you could put it into the calculator. Um, but they will ask an index law question. Definitely. I'm surprised it wasn't on the non-calculator. So really expect it to come up in this part. So no, you're going to need to know stuff like x to the 0, which is 1. You're going to need to know x to the a minus x to the a divided by x to the b, which is x a minus b. Again, x to the a times x to the b, which is x to the a plus b. You're going to need to know all of these things, okay? So yeah, make sure you really learn that. They're quite easy marks once you learn them. Uh, don't dish away marks that you can get. I mean, yeah. But yeah, anyway, so that topic is a key one. But yeah, let's move on to this one. So this is a tricky ratio question. I think you're going to get something like this as well. Every paper has a ratio question in. Usually like an easier one and then a harder one. So we did an easier one earlier. With the what was it? With the we just did it actually. Did the lava stuff, and stuff like that. Where you just scale it. This one's a bit more involved. Let's read it. So the ratio of martyrs' hourly pay to Khalid's pay is 6 to 5. Then they get an increase of 150 to the hourly pay. Then the ratio goes to 30 to 11. We need to find the exact hourly pay before the increase of both of them. Okay, so the key thing you need to note here is initially the ratio is 6 to 5 to, well, martyr to Khalid, I should say. The ratio of their pay is 6 to 5. That is not saying that martyrs pay £6. That is not what this is saying. This is saying that their pay simplifies to 6 to 5. So, for example, say if we had a pizza, right, or something of 4 slices. Say if I have 2 of them, that would be 2 over 4. But actually, that also simplifies to a half, which makes sense as well because I had half of the pizza. But in reality, there were 4 slices, not 2. So this is the true fraction, right? This is what is actually going. They're both equivalent fractions, but this one's the actual fraction that happened, right? They're words for slices, not two. Even though they mean the same thing, they are not identical. You know what I mean? It's the same thing here. What we need to do then to find the actual pay, we need to times by some scale multiple x, such that Marta's pay then is equal to 6x and Khalid's pay is 5x. Okay, because of the fact that we do not know what the actual amount they earned was, but we know it scales to 6 to 5. So if we add this scale factor, this factor x, to give us the true what their true pay was. Okay. So that's the idea with these ratio ones, is to times by number x to give you the true amount of something. Okay. But obviously, bear in mind this does simplify back to 6 to 5 because we can just cancel the x's. But we want to times by an x to give us the actual pay. Okay. Hopefully you can see that. So then we can deduce this, right? Their pay in terms of x. Okay. But then we are told that they get an increase of 150. So we add in 150 to both of them. So 6x was 150 and 5x is 150. And then we are told that this is now in the ratio 13 to 11. So now we've got two equivalent ratios. We can simplify this, can't we? I'm going to... yeah, so we can then say, well, oh no, no, we can't simplify it. We'll leave it there. So that's our ratio, right? So we have one ratio here is equal to another. Okay. So we essentially need to solve for x, because then if we find x, we can find the actual pay, can't we? This is the pay before any increases, right? As we just discussed. But then how do we deal with this? These two ratios equaling each other. How do we get some sort of equation? Again, there are multiple ways depending on how comfortable you are with ratios, but this is how I approach it. Always. When two ratios that are different numbers, it's hard to compare. It's hard to see what you equate together. But when two ratios have one number in common, say if you have one that's in both of them, for example, for some number n and m, that means they are identical, so we can compare them directly. So we can say 1 is equal to 1, wow, clearly, but also n has to equal m in this case. That is what we're going to do here. So we have 6x plus 1.5 is equal to 5x plus 1.5. That's going to be 13 to 11. Okay. But I want to compare them, the two ratios. So I need to make two numbers common. The best way to do this is to divide the first number in the ratio. So if I divide the first ratio by 6x plus 1.5, that's then going to be 1 because I'm dividing by itself. And that's going to be 5x plus 1.5 divided by 6x plus 1.5. Don't be afraid of out of fractions like this. Don't be afraid. Okay, hopefully you can see that. So I'm just essentially scaling by 6x plus 1.5 to get 1 here. I'm going to do the same here. So I can divide by 13. So the first number on each. So that's going to be 1 to 11 over 13. Now they're both are exactly the same ratios. Because we made the two ratios the same, we can compare them directly. So that means then we can deduce 5x plus 1.5 over 6x plus 1.5. That is going to be 11 over 13. And then this is just solving an algebraic fraction. So we can cross multiply to say 13 lots of 5x plus 1.5. It's going to be 11 lots of 6x plus 1.5. And now we are going to expand the brackets. So 13 times 5 is 65. x, and then 13 times 1.5, 19.5. I'll do the calculator on the screen, but it's just quicker to do it on my phone. Plus 19.5, and then we can expand this one. So 11 times 6 is 66 x, and then 1.5 times 11 is 16.5. So now this is just a linear equation we can solve for x. Well, if we take away 65x both sides, we're just left with 19.5 equals x plus 16.5. So then to get x on its own, we can then subtract the 16.5 next to it to just be left with x equals 3, right? 19.5 minus 6.5 is 3. But that's what we wanted. We found x. Because now we know their pay, remember, is initially 6x and 5x. So therefore, Marta is going to be 6 times 3, which is 18. And Khalid's is 5x. Now 5 times 3. X is 3. So that's going to be 50. So then it's going to be 18 and 50. Cool. Okay. Yeah, it's a very tricky ratio question, that is. But the key thing you need to appreciate here is to scale a ratio to the actual amount, you just times by a number. So then we find this missing number to then find the actual amount. Okay, cool. And also bear in mind this trick with fractions, right? With ratios, if you have two ratios equaling each other, you can compare them by making a number common to both. The best strategy that always works is dividing by the first number, for example, on each side to then get 1 to something is equal to 1 to something else. So that means these two bits have to be equal to each other, so we can compare them, and then you solve from there. Okay. Uh, One question 11 now. So we are told Tarek buys a laptop. He gets a discount of 5% off the normal price. He pays 551 for the laptop. So he hasn't. So the So it works at the normal price. So the price before any discounts. So this is a reverse percentage question. The best way to tackle this is again to just let x be the original price, right, and then work from there. Okay, so that's the original price. So then a discount of 5%, so that means it's worth now 95% of the price. How do we 95% as a decimal? Again, you divide by 100, that's 0.95. So we're going to times by 0.95 to get 95% of the price. So that's going to be 0, and then we are told the discount is the price of the laptop after is 551. So now we just solve for x, which is the original price. So x is going to be 551 over 0.95. And that we put that into the calculator. Which is 580. Okay. For 2 marks. So that's the sort of method, right? You can, again, people have their own methods. If it works for you, that's great. I think people might panic a lot. I think if you don't let x be the number, you think, oh, how do I go backwards here? Oh, I'm not used to it going the other way, like, and then they freak out. But if you just use the normal method, just let x be the number. Do how you'd normally calculate percentage reduction or whatever. Then you just use algebra to find the number, and it's quite simple, really. Well, relatively anyway. Just don't be afraid of algebra. But yeah, it makes life a lot easier if you do it this way, in my opinion. But yeah, that's for 2 marks. Hopefully, that should make sense. Okay. Okay, now we are given another bit. So we are told that Joan invests £6,000 in savings account, and the account pays a compound interest of a rate of 2.4% in the first year and 1.7 per year for each year after. So then it says work out the value of the investment, so how much she put in, how much is in the account after 3 years. Okay, so compound interest essentially means a percentage each year, right? It increases by a percentage amount. Which is what we've got here, right? So 2.4 and then 1.7. So obviously you can do this in one easy line of working if you're really, really confident, but I'll break it down. So £6,000 is the original price. Then it says in the first year it's 2.4%. 2.4%, remember, if you divide by 100 as a decimal, because remember percentage just means per 100. So to get the number, the decimal equivalent, you just divide by 100. It's like and it's like why we have, for example, 75% is 0.75, which is obviously 3/4. Okay, for example, because we just divided by 100 to transition between a percentage and a decimal. Okay. So then to divide by 100, you get 0.024. Move 2 decimal points away. Here. So that's 0.24. And likewise, 1.7% divided by 100 is going to be 0.017. Okay, so what's going on here is this has been added on each year. So 2.4% has been added on. So it's going to be 1 adds this amount of 0.24 or 0.024. Because obviously it's not this add 1, because obviously 1 represents 100, the whole amount, the original amount, and then we add in 2.4% on. So this 2.4 is this decimal here. So then doing this is equivalent to adding 2.4%. Okay, these percentage questions are much nicer when you get comfortable with multipliers. Okay, so you convert a percentage to a decimal. Okay, so if you work that out, so that's after first year, so 6,000 times by 1.024, you get 6,144. That's at the end of first year, right? Because we have to apply 2.1% in the first year. And then what about the end of the second year? Well, this number then, 6,144, then 1.7% extra in the next year. So that's going to be 1.017, right? From this number here. So we work that out into the calculator. Then that would be this number here, 6248.448. And that would be the end of second year. But it wants the end investment in 3 years, so we need to apply this again. So then 6248.448. Again, it's 1.7% extra, so at 1.017. That's going to be, if you times that by 1.017, you get this number here, 6354 .67. I'm going to round that to the nearest pence, right? And that should be answer, right? Because that's at the end of third year, which is what we're after, right? The end of 3 years here. So that's 6354.67. Okay. I did say at the start that if you are confident, you can do it quicker, and it's this. So if we have the original amount, well, actually, at the end of first year, it's 2.4%. That's going to be 1.024. But then this amount is being raised by 1.7, which is 1.017. That's at the end of second year, but then we're doing it again. We're timesing this number again by another 1.017 to get the third year. So that'd be squared. And this one line will get you 6354.67. That's if you, and that's the quicker way. Well, it's the same way. It's the exact same numbers, but I'm just doing it all in one go. But this is the step-by-step approach here. That hopefully should be clearer. You can do it this way for 3 marks, but if you're really, really confident, then you can go for this line of work in here. Okay, cool. So that's question 11. Um, wasn't that question 10? No, question 11. Okay. Okay, question 12. By the way, there were 22 questions here, so we've got through most of it already now. But obviously, there are more marks towards the end, but we'll get onto that in a minute. Okay, we're on question 12. So this is 2 marks. So it says Jeff is choosing a shrub and a rose tree for his garden. The garden centre, there are 17 types of shrubs and some rose trees. Okay. He says there are 215 different ways to choose one shrub and one rose tree. Can he be correct? Okay. So with these type of questions as well, a really good exam tip is to work out what topic this is asking for. And actually, this is asking for different ways of choosing stuff. So this is a combination, or some call it a product rule question. Okay, so it's asking for how many different ways we can choose something. Well, imagine you have a list of shrubs, which are 17, right? 17 different types of shrubs. And we have a list of rose trees, right? We pick from each of these, we pick one from each list. And we need to essentially consider how many possible choices we can make. So each shrub, say we pick the first shrub, there are then some amounts of rows, so the X amount of rose trees, right? So the X amounts of there. Then the second one, there'll be again X amounts to pick from. The third shrub, there'll be X amount to pick from. The fourth amount, there'll be again X to pick from. And the fifth one, there'll be X amount. So we do that. So for each shrub, there was X amount of rows, but there are 17 different types of shrubs. So that's going to be 17 times by X. That is how many total choices there are. And this is what's called the product rule, because when you're picking combinations of two from two different lists, right? One from each list, you are just timesing the amount of each list together to get the total amount. Because for each shrub, there are X amount of choice of roses. So for the first one, there'll be X amount of roses to choose from. If you pick the second shrub, there'll be X amount to choose from. And the third one, there'll be X amount. And actually, it goes on. And that'll be 17 times, right? Because there's 17 shrubs. For each shrub, we can then pick X roses. So the total amount of choices is all of this, and that's just going to be 17 times X, right? Because there's 17 lots of X. But that's the idea behind that. But really, you should recognize these and times them together. So 17 times X, that's the total combinations, and we are given that's 215. But it said, can he be correct? Well, if it can be correct, let's consider what the number is. So then X is 215 over 17. And that will be a fraction. Okay, 12.647 something. But actually, this is not a whole number, is it? And it has to be. So it's not an integer, should we say, which just means a whole number. But it has to be a whole number if it was possible, because you can't have like half a rose tree, can you? So it cannot be an integer. This is not an integer. So Jeff is not correct. So there cannot be 215 ways, because you have like it's saying there are a decimal amount of rose trees, which isn't possible. It has to be a whole number. So yeah, that's the approach there. Just recognise it's a combination question because it's really asking for about different ways of choosing something. So then you should be thinking times in the amounts together from each list or from each category to get the total amount. Okay. Okay, we're on question 13 now. I think this is a fairly simple question that I do love asking this every year. In my opinion, it is 3 marks. Well, I mean, it literally is 3 marks, but I mean, free as in not costing anything. Because it's just expanding. Like, hopefully by now, at least at the higher end of the paper, you should be fairly comfortable with expanding stuff. So triple brackets works in the exact same way, really, and it's just 3 marks. It's a bit of a grind to work out all the terms and stuff, but we can get there. Uh, so yeah, so expand and simplify. So when you have triple brackets or any amount of brackets, really, you just do it one part by part. So you should know really, we know how to deal with double brackets, don't we? So let's do the first two, x minus 2, 3x plus 2, and then let's work that out. So that's going to be, again, if you have your own method, so that's called, some people use FOIL or whatever. So really, you're going to x times 3x, which is going to be 3x squared. Then you're going to do x times 2, which is going to be plus 2x. Then you're going to do minus 2 times 3x, which is going to be minus 6x. And then you're going to do minus 2 times 2, which is going to be minus 4. And we can simplify this to get 3x squared minus 4x minus 4. Okay, but that's this bracket here, x minus 2, 3x plus 2. This then all has to be times by a 2x plus 3. So this whole thing then has to be times by 2x plus 3. And we're going to do the same thing here then. So there's more terms in this bracket now, but oh god. But again, we just times term by term. So 3x squared times 2x is going to be 6x cubed. Then we're going to do 3x squared plus times 3, which is going to be plus 9x squared. Then you're going to do minus 4x times 2x, which is going to be minus 8x squared. Then you're going to do minus 4x plus times 3, which is going to be minus 12x. Then you're going to do minus 4. I don't know the best way to do this. Minus 4 times 2x, which is going to be minus 8x. And then a minus 4 times 3, which is going to be minus 12. And then it says we've got to simplify it. So there's only one x cubed term. That's going to be 6x cubed. Bring all the x squared terms together. So it's going to be 9 minus 8, which is going to be just 1x squared or x squared. Then the x terms, so minus 12 minus 8 is minus 20x, and then minus 12. And that should be your answer, right? Cool. So yeah, I don't know, there's not much to say here. If you have your own method, go for it. I know some people like doing a grid method, whatever works for you. But really, all you're breaking it, you just the main method here is to break it down into double brackets, right? Because you know how to expand double brackets. And then you just do it one part by part, right? So you do the first set of double brackets, and then you times that bracket here by the other bracket 2x plus 3. And then eventually you get the whole product, right? Okay. I'm going to move on then. Question 14. We are given the first 5 terms of a sequence, and we need to find the nth term. Now, exam strategy tells me it's going to be a quadratic nth term because it's near the end of the paper. Well, yeah, near the end of the paper anyway. And it's 3 marks. You don't get that many marks for a linear. But if you're a bit unsure, there are only two nth terms. Well, no, there are 3 nth terms you need to be aware of. A linear, a quadratic, or a geometric. Now, it can't be a linear because it's not going by the same amount each time. Geometric, well, you would have to divide the second by the first term and then the third by the second. But 11 over 4 is not the same as 22 over 11 because that would be 2 and that would be 2.75. So it has to have a common ratio, but there is no common ratio. So that means by elimination it has to be quadratic. But normally they tell you it's a quadratic, but really there's only a certain amount they can ask for, really, in terms of nth terms, and it's going to be a quadratic because it can't be a linear and it's not going to be a geometric. So either it's a linear or quadratic. They're not going to be mean and expect you to work out a geometric sequence. Well, I hope not. So by process of elimination, because it's not going up by linear amount, it has to be a quadratic sequence. So a quadratic nth term. Well, that's a UN, so that's our nth term. So if it's a quadratic, it's going to be looking like this form, isn't it? An squared plus bn plus c. That is a quadratic, right? In the same way, a linear looks like this: bn plus c. It's linear, right? So it's like a straight line of the form mx plus c. It's the same sort of form, but hopefully you recognise this is a quadratic. This is a generic form of a quadratic sequence. So then our mission is to find these coefficients a, b, and c. Okay, so how are we going to do this? Well, I'm mainly just going to give the method here, at least method that works for me. The common method that I've seen, most people do, I think. There are many ways to approach it. Like I said, with everything else, if you have your own way, it makes sense for you and you do it well, by any means, just do that. Right? Hopefully, you get the right answer at the end that I do. But how I approach this, without not going into why it works, I'm not going to do that here. But what you do is, well, consider the sequence again, 37, 56. What you're going to do then is consider the difference. So it's kind of like with normal sequences, bn plus c that are linear, you consider the common difference, what it goes up in each time. We're going to do the same here. We're going to work out the difference of this sequence, which is going to be, well, the difference here is going to be 7, isn't it? 4, 4 plus 7 is 11, yep. And then 11 to 22 is going to be 11. Then 22 to 37 is going to be 15. Then 37 to 56 is going to be 19. Okay. 37 and 19 is 56. Cool. But actually, if we did this approach, if it was a linear sequence, this difference would be the same each time, but it still varies. But actually, then we consider the next difference. So that's going to be 4 between 4 and 11. 4 and 4. And what you notice is now it's the same. So it's kind of like, because it's quadratic, in very, very informally, although not correct, but I'm just saying, because it's like a next power of n, you do the second difference rather than the first, and then it becomes the same. But yeah, that's the approach. You consider the difference and then the next difference. Okay. So this will be a common number, right? The same number. That will always be this case. Always, with a quadratic nth term. So then what this tells us actually that 2a, I guess because it's a second difference, so it's 2 lots of a. That's not the reason, but that's where you can think of it. 2a, so that's the first diff. Let's just say the first difference, and the second diff is here. So then 2a is equal to this second difference 4. And then you solve for a. Well, a is 4 divided by 2, so a is 2. Okay, so I found the first part. So that means our nth term must then be 2n squared bn plus c. So we now need to find b and c. What I'm going to do then is again write down the sequence. So 4, 11, 22, 37, 6, 56. Then I'm going to write down the sequence 2n squared. The way you get this sequence is by substituting n is 1 and then times by 2, obviously. So 1 squared times 2 is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. And then 4 squared is 16 times 2 is 32. And then 5 squared is 25 times 2 is 50. And then what you're going to do is do the difference between the two. So 4 minus 2 is 2. 11 minus 2 is 8. 11 minus 8 is 3. 22 minus 18 is 4. 37 minus 32 is 5. And 56 minus 50 is 6. Very, very briefly, why this... oh, actually, hang on. I'll talk about that in a minute. So then actually notice this is now a linear sequence. And that's what I was going to explain. I'll explain in a second. This is a linear sequence, and in particular, it's this one here, Bn plus c. That is a linear nth term, right? And that's this nth term here. But what's the nth term of 2, 3, 4, 5? Right, it goes up in 1, so it's going to be n. And then go backwards to 1, it's going to be n plus 1. Okay, that's the nth term of it. Hopefully, you should be very confident of working out nth term of a linear sequence, and that's this. So Bn plus c is n plus 1. So therefore, the final nth term of un, you don't have to call it un, you just say it's 2n squared plus n plus 1. And that's your final quadratic. The reason why this works, however, very briefly, is because this top sequence here, isn't that just this one here, 2n squared plus bn plus c? If we are taking 2n squared plus bn plus c from this sequence 2n squared, well, the n squares cancel, and in particular, you just left the sequence bn plus c, which is why this is A, a linear sequence, and B, it's exactly bn plus c, this sequence here, because that's what you get from subtracting the original sequence from the 2n squared sequence. But yeah, that's the idea going on, but I'm not going to go too much into that. It can be quite intricate, but that's the method. Okay, so you consider the differences, then you get 2a, I guess because it's the second difference, it's 2 lots of a. Again, that's just a way to remember it, not the reason, but that's necessarily. But that is the that's how you can remember it. 2a, but it's this number 4, so then divide by 2 to get a. Then you subtract by the n squared part, the sequence, and then you get your linear, and then you there we are. Okay. We're on question 15 now. So we are given an iteration formula, and we're given xn plus 1 is the cube root of 10 minus 2xn. Made that a bit nicer. There we are. And we need to use the iteration formula to find the values x1, x2, and x3. And we need to start with x0 is 2. So what all iteration formulas tell us is if we have the starting number xn, we can find the next value of n because it's n plus 1. So if we substitute x0 into here, so cube root, oh god, the cube root of 10 minus 2x0, well, the next number, n plus 1, 0 plus 1, that's going to be x1. And that's going to be our first value, x1. So then we just substitute x0 is 2 into here. So it's going to be cube root of 10 minus 2 lots of 2. And so you plug that into the calculator, the number's going to be the cube root. So we have to shift here because that to get the cube root. Hopefully I can see. So here, it's a square root normally, this root button, but to get the cube root, you need to shift and then pick the yellow option, which is cube root. So we're going to do the cube root of 10 minus 2 lots of 2. And that gets you this decimal here, 1.817. I'm going to write it all down. 1.817, 120593. Okay, so that's x1. Then x2, we're going to reuse it then. So we're going to plug x1 into xn now to get x2. Well, actually, we don't have to write the number again. This is now arms, right? If we click the answer button, that's your previous answer. So what we can do is to reuse it, we can say that's the cube root of 10 minus 2 lots of xn, which is going to be ands, right? So that will, that because the ands button, this is now ands, right? That's x1. So we're basically plugging in the previous answer to get the next one. That's what this is doing. So an x2 would be now 1.85 331 8496. And then x3, because now that's the previous answer right now. X3, then you plug it in again. So we just click the equal button because now ands is now x2. So now to get x3, we can just do this again. To then get 1.84 626. Oh, 626. 5953. Okay, now it doesn't say to any degrees. I'm going to say to three decimal places. That's what I'm going to say because we can't put it all on the answer bit on the end. So x1 is 1.817 to I'm going to say to 3dp. Okay, x2 is going to be 1.853. X3 is going to be 1.846. Okay, all to three decimal places. Cool, so that's just using iteration. Hopefully, again, that should be fairly standard. But instead of, remember, if we trick the calculator, just use the answer button instead of just putting you answer it back in again, writing it all down. Because the answer is the previous answer that you got. So you're just reusing the answer. And if I keep clicking equals, what will happen eventually is it will then converge to a certain number. See, I'm clicking equals now, it's staying the same number because to that many degree, that's what the root, the solution goes to. This number here, 1.847 something. I'm clicking equals and it doesn't change. And that is the whole idea of these iteration questions, right? That you will converge to the number, right? You will go towards a number after so many tries, right? But yeah, those are the first three values. Okay, for 3 marks. And then it says the values of x1, x2, and x3 that we found are estimates of the solution to an equation that looks like this: x cubed plus ax plus b equals 0. So it's the same solution, the same three. What that means is that um, this part here has to be the same as that cubic. We have to transform this into a cubic: x cubed plus ax plus b. How are we going to do that? Well, I'm gonna note that down again. I'm gonna say xn plus 1 is the cube root of 10 minus 2xn. So how are we going to get a cubic? Well, that has to rearrange to a cubic. Well, we're going to cube both sides, aren't we? We're going to say x cubed. Now remember, xn and xn plus 1, they're both x's. So we can just get rid of the n plus 1s and the xn's here. So x cubed is now 10 minus 2x. And then we put it all equal to 0. That's going to be x cubed plus 2x minus 10 equals 0. Oh, hang on, what's happening here? X cubed is equal to 10 minus 2x. Cool. And now this is the cube that they want. So A, if we compare, A is going to be 2 and B is minus 10. Okay, and that's also, by the way, give another brief explanation. That is how these iteration formulas work. Because you can if we have multiple x's in the equation, you can rearrange to make x almost like the subject of the formula. So what they've done here is is they then said x cubed is 10 minus 2x, and then they cube rooted it to say x is the cube root of 10 minus 2x. And that is what they've got here, right, that we had to start off with. That is how they've got from here, from the cubic to the cube root. So we've got x in terms of x. What this says is if we make this the original, the initial value, then we can get the next value, and then it will slowly converge to the root, right? To the roots, to the root. So what this is saying is, as a result, if we apply the iteration formula to get the solution for x here, well, that is the exact same as the solution to this cubic here. This x cubed plus 2x minus 10 equals 0, because they are the exact same equations, right? We just manipulated it. But these they stem from the same equation. So the root for this is going to be the root for this cubic. Okay, and that's where it comes from. So you just rearrange to get x in one way equal to something else. Okay. Um, let me just write that down again. X cubed plus 2x minus 10 equals 0. So then if you compare, the a is plus 2 and the b is going to be minus 10. Okay, cool. Okay, we're on question 16 now, and we are given two triangles that look like a paper airplane. I don't know. They're given two triangles. We need to calculate the length of QS. So if you have a missing thing that we need to work out, just call it X. It makes life easier. Believe it or not. Okay, so this actually screams sine rule, cosine rule, and half A B sine C, because these triangles they're not right angles. There's no right angles in them, so we cannot apply the usual trig of SOHCAHTOA and Pythagoras here. So we have to use the sine rule, which is sine, or I guess A, over sine A equals B over sine B. And the cosine rule, which is obviously A squared equals B squared plus C squared minus 2BC cos A. I think they're both in the formula, but you do need to know how to apply them anyway, and you'll see in a minute. But yeah, so you're going to need to remember these formulas. You probably have to use it here. These will work for non-right angle triangles. So when you don't have a right angle triangle, SOHCAHTOA and Pythagoras break down and you cannot use them. So you have to resort to these formulas instead, which is what we got here. So with this in mind, can we work out x at the moment? I don't think we can, because we do not have two sides known, so we cannot use the cosine rule. And we can't use the sine rule either, because we don't know any sides actually. So we can't use either side. We can't use either. We don't know. We don't know any sides, but we know two angles, so that might help. Okay, but this is connected to this triangle here, QPR or PQR. But here we know two sides and an angle. So actually, that could either be the sine rule or the cosine rule. But what do we want to work out? Well, we need a length. So we're going to need this length here, which is QR. So if we want to find, if we know two angles, an angle and two sides, and we want to find a side, it's going to be the cosine rule. Okay. We do not want another angle, so we do not need the sine rule here. So QR then, we can call that Y if you wanted to, but I'll call it QR. So that's going to mean QR then, if you substitute it into here, well, the missing angle A, which is QR, squared, that's going to be the other two sides squared, 9.4 squared, add 11 squared. That's going to be minus 2 lots of 9.4, 11, cos of the angle opposite. So 27 here is facing this angle, this side QR. So it's going to be the opposite angle. So it's going to be 27 degrees. And therefore, you put that into the calculator. That's going to be 9.4. Hang on, let's shorten this. Hang on. Uh, oh, bugging out. I need to make this smaller. Okay. I'm going to need to make this smaller. There we are. Makes my laptop freeze out. This calculator's too big. Okay, anyway, so that's going to be 9.4 squared. Hang on, let me check. Okay, I think the stream's okay. Okay, I thought it would have shut off the stream there. That's good. Okay, so that's going to be 9.4 squared. Add 11 squared. Oh. That's going to be minus 2 lots of 9.4, 11 cos, which is going to be here, of 27. And that should be in degrees. Okay. So it's going to be this here, 25.0998, 508. Make that a bit clearer. But this is QR, and this is 9.4. Don't know where that came from. 9.4. But that is the square. So that's QR squared. So therefore QR is going to be the square root. So we're going to want to root this. So it's going to be root 25.0998, da 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 da, so on. So if you square root that, our answer, that will get us this number here, 5.0099975, and so on. Okay. So that's QR. So now we know this length here, which is now, for this on the diagram, 5.0099. Okay. So we know this length here. And we also know two angles. So if we want to find a side, we know a length and two angles. If we have two angles, that's going to be the sine rule. And if we have three sides, it's a cosine rule. That's the quick way of knowing which rule you need to use. Okay. Here in the first triangle, we're dealing with three different sides, so it's the cosine rule. Here we have two angles, so it's going to be the sine rule. So now we know this side, so 41 is opposite to this side here, QR, which is 5.0. And we know this 88 angle is opposite to X, which we want to find. Sine rule, right? So now we're going to apply the sine rule. So that's going to say X over sine of its opposite angle, which is going to be 88. And that's going to be equal to the other number, the other side, 5.0099, so on, that we just found out. All divided by sine of that opposite angle, which is 41 degrees. Okay. Because the 41, this angle here is facing this. The other side, so yeah. So that's the thing. When you're using the sine rule, the thing you need to pay attention to, this angle here, actually I probably should say it's little a over the big A here. Just to make it consistent, because that's what they use in the formula book, I think. But yeah. So the angle you're using here for the length is the opposite angle. Okay, so 41 is opposite to the length here, and 88 is opposite to the angle x. So that's why we've done what we've done. Okay, well this is just solving for x now. Really, we can actually work out this fraction 5.00 divided by sine 41 via our calculator. So that's going to be divided by sine of 41 in degrees. And so that's going to be this number here, 7.63 647, and so on. And so this is still x over sine 88. Now, how do we get x on its own? Well, we need to times both sides by sine 88. So therefore, x is going to be sine 88 times by 7.63647. And so then you just times that answer that we got by sine 88. And so then you get this answer here, which is 7.63181, so on. And that's in centimeters, I believe, right? Hang on. Okay, cool. Yes, centimeters. It said give your answer correct to three significant figures, so we need to round it to three sig figs. Well, to three significant figures, 7.63, right? Because the one will not round it up because one is less than 5. So 7.63 to three sig figs is our answer here. Cool. Okay. Question 17. So hopefully that's clear, right? So when you're dealing with non-right angle triangles, again, there's only a limited amount of tools you have. So it's either the sine rule or the cosine rule. Bear in mind the area is a half AB sine C. So for the example, the area of this triangle would be 11 times 9.4 times sine 27. The angle in between the two of them, okay, and halve it, okay. But that's not what we asked here. So we need to find the missing length x. But to go through it one last time, we didn't have this length here at first. We only had two angles and no sides. We don't know anything about any of the sides. We can't use either rule. So then we look at the other triangle and we're given two sides and an angle. We need to find the third side. If we are dealing with three sides, then it's the cosine rule. So that's how we can find this side here. And then once we found this length here, because now we know two angles on the side, because we have two angles, now we can use the sine rule. And that's the key point. So I guess I'll say sine rule means you're dealing with two different angles, right? And the cosine rule is going to be three sides. If you're dealing with three different sides, all the three sides, triangle, it's cosine rule. If you're dealing with two angles, it's a sine rule. Okay, that's just a general, like, a little tip with that. But yeah, so we went through there, and we got to the answer. So that's sort of fairly well. It's a bit of a lengthier type sine cosine rule question. You're just combining two of them together, but it shouldn't be too bad. Okay, one question 17 now. Okay, but to show that this subtraction here is equal, can be written in this form. Okay, so what we're going to do is, well, we're just going to subtract the fractions, okay? So we've got three different things going on. We're subtracting this fraction by this one, and then we're subtracting it by minus 1. So we're going to do it step by step, piece by piece. So first thing, we're going to do 3x over x plus 2 minus 2x plus 1 over x minus 2. We're going to do the first subtraction first. We won't worry about the minus 1 just yet. Okay, so what we're going to do here, well, like with any other fractions, you can get a common denominator by timesing by each of them. So x plus 2 here, we're going to then times by both top and bottom by x minus 2. So 3x of x minus 2, that would be x plus 2, x minus 2. The reason why that works is because we timed both top and bottom by x minus 2, yes, we've got a common denominator, but that would simplify to this fraction still, because we can cancel out the x minus 2s to be left with 3x of x plus 2. So that's why that works. But we're doing this to ensure we get a common denominator, because when you subtract the two fractions, as you remember, you need a common denominator first before you subtract them. But that's what you're doing. Cool, so that's 3x of x minus 2, then minus 2x plus 1, and then we're going to times by the opposite denominator, which is going to be x plus 2. And that's all going to be x plus 2, x minus 2. And that will go to, and then you, because we've got the same denominator, we can just subtract the top number, right, the numerator. So we leave the denominator as it is. So then we're going to left with 3x x minus 2 minus 2x plus 1 x plus 2. Okay, we're going to have to work this out. So the best way, really, well, not the best way, but the way is to we're going to have to expand and simplify, aren't we? So we're going to have to do some rough working. I say woof, like a dog. I don't know what I'm thinking. So let's work this out. So 3x x minus 2 minus 2x plus 1 x plus 2. So the first bit is going to be 3x squared. This should be a fairly nice expansion. If it rubs out anyway. So that's going to be 3x squared minus 6x. And then we're going to minus this expansion here. So this is a double bracket. So that will go to 2x squared plus 2x times 2, which is plus 4x. Then plus x, then plus 2. So then that will simplify to 3x squared minus 6x minus 2x squared. Okay, minus 4x minus x, that's minus 5x minus 2. So then that simplifies to x squared. 3x squared minus 2x squared is x squared. Minus 11x minus 6 minus 5 minus 2. And then therefore this whole fraction becomes x squared minus 11x minus 2 over x plus 2 x minus 2. Okay, I'm going to rub this out now. Hopefully that's just expanded simplifying. You would need to write this down, I think, but I need to make some room. So I'm going to do the next bit up here. Okay. Actually, no, I could make room. Never mind. I could create more room, but I forgot. I'd leave it there. But that it simplifies this whole numerator to this here. Okay, hopefully that's clear. But now we did this part then, didn't we? Now we need to subtract this by minus 1. Okay. So that means x squared minus 11x minus 2, our fraction we got, over x plus 2, x minus 2. We have to subtract minus 1. So then that's going to be, well, if we're minusing 1, we just have to times top and bottom by x plus 2, x minus 2. Because we had the common factor, I guess the denominator is 1, right? So then we have to times top and bottom by both x plus 2 and x minus 2 to get the common factor. Okay. So that's going to be x squared minus 11x minus 2. Then it's going to be minus x plus 2, x minus 2, all over x plus 2, x minus 2. So then we're going to need to expand x plus 2, x minus 2. So that's going to be x squared minus 11, x minus 2. Minus, well, the expansion is going to be x squared. X times x is x squared. X minus 2 is minus 2x. X plus 2 is 2x. And then minus 2 times 1 is 2 minus 4. But you should recognise this is actually going to be a difference of 2 squares. So the 2x's cancel to just left with x squared minus 4. So then that will be all over again, x plus 2, x minus 2. Okay, now I'm going to create some more room. Okay. Okay, hopefully there should be enough. Oh, okay. I don't know. Oh, God. Okay, I didn't mean to create that much room. I don't know. Okay. Okay, so I'm going to bring this over here now. So I'm going to simplify. So it's going to be x squared minus 11x minus 2. Then minus x squared minus 4 is going to be plus 4. You can see up here. Minus x squared plus 4. Okay. All over x plus 2x minus 2. So then that will simplify to the x squared cancel. So you're left with minus 11x. Minus 2 plus 4, that's going to be plus 2. All over x plus 2, x minus 2. Okay. But the last thing you should notice is, I mean, we did it earlier actually, just this is actually a difference of two squares. So we can expand this out. So that's minus 11x plus 2. And that's going to be x squared minus 4. Okay. And that should be the answer, I think. What's it say? In the form ax plus b over x squared minus 4. Yeah, so a would be minus 11 and b would be 2 here, over x squared minus 4. Okay, so that's how you expand it, really. That's how you deal with algebraic fractions, especially like this. They love asking like three different fractions, so you do it bit by bit, like we did with triple brackets. You do the first two fractions first, subtract them two, then you subtract that fraction by the remaining number, which is minus 1. And then overall, you should get this fraction. Okay. Yeah, and the key thing here is to realise when you're subtracting, you need to have the common denominator in both of them. The best way to do that is to times by the opposite denominator on both on the opposite fraction. So, for example, like to recap, x plus 2. To get the common denominator with this fraction, you're going to need to times top and bottom by x minus 2, which is what we've done here. Likewise, with this fraction, we need to get the other denominator of x plus 2 times top and bottom, and you get that. And that works because, as I said, you can cancel out the x minus 2, for example, and then you're left with the original fraction. But it's best not to do that here. Because we want to keep the x minus 2 to get the common denominator. But anyway, that's how that works. A lot of algebra there, but it still should be fairly, I don't know, fairly standardish. Hopefully, if you practice algebraic fractions and simplifying them, it shouldn't be too bad. Just a bit of work. Okay, question 18. Um, November. Okay, so we are given a graph of sine x, and we are told to find the solutions to sine x is 0.6. Now, actually, what this is saying when you solve stuff like this, you need to find the values of x where sine x is 0.6. So, it's going to be here, right? 0.6 is here. So we're going to need to read off the graph at the points where sine x is 0.6. And actually, hopefully this should work. But I've got a ruler thing here. Oh, God. Uh, it's not turning the way I want it to. Okay. Oh, God, we'll get there in the end. It's going back. What? I'm not making it go backwards. What's going on? There we are. We'll get there in the end. Oh, God, now it's zooming that out. Oh, my God. Uh, let's go to 100 again. Oh, bloody no! I'm gonna move the ruler. Ah, uh, what, what? Oh, why is it? What is going on? Uh, I don't know. Why? Why is it not working the bloody way I want it to? I tried to be creative for once, and then it just gets screwed over. There we are. Okay, we got there. Okay, so put the ruler flat like this. So the way you can read off is essentially put the ruler where y or sine x is 0.6, which is going to be here, right? So 0.5 is there, so 0.6 is the next set of squares here. So then you need to find essentially where the this ruler, when it's at 0.6, crosses the curve. So it's going to be like here in it and here. So now I'm getting rid of this bloody ruler. It's caused me a lot of grief. um, okay. So we use the ruler and it crosses here, roughly. So then we need to read off, well, where does the curve cross this line bit? Well, it's going to be here, isn't it? If we read off the axis, it's going to be there. And uh, about there, isn't it? Yeah, okay. So then if we read off the graph, the axis, well, it's going to be here, right? And here. But we need to work out what value of x this is. So again, it's kind of like the box plot scenario. We need to work out what each box or square represents. So one box. So there are three sections, right? So three main boxes, three big ones. So 1, 2, and 3. So let me write that clear. So one box, two boxes, and three boxes that equal 90. So three big boxes equals 90. Then one big box is 30. But each mini box here, there's 5 boxes, right, in each big box. So that means one box is going to be 30 divided by 5 to give us 6. Okay. So each box represents 6 degrees. So then if each main, so this is going to be 30, the big one. So then the next box forward is going to be 36, isn't it? So that means the first solution is going to be 36. Likewise here, well, 180 is here, so that means this main one's going to be 150. Then the next box to the left is going to be 150 minus 6. So that's going to be 144. Okay. Um, Let me just make that more clearer. What's going on now? Okay, so hopefully that makes sense. So one big box, each big square is 30 degrees, but there's 5 little boxes or little cubes in each big one. So one small square, or say one small box, I should say, is worth 6 degrees. Okay. So then you read off the graph there. So that's 6 boxes. So 30 must be a big one. So the next one's 6 after 36. And then that's going to be 144 because that's 6 less than 150. Okay. So those are the two crosses with the graph, but it says 4 solutions, not 2. But actually, notice that our interval is between 0, so it starts at 0 here, and then 120. But the graph here ends at 360. But actually, they've done that because you should know that the sine graph repeats every 360 degrees. So the next two solutions are going to be another 360. So we're going to do 360, add 36. and that's going to give you 396. And then the next one's going to be 144, add 360, and that's going to be 504. Okay, and those are our two solutions in 720, because 720 is 360 times 2. So to get the next two solutions, we need to add 360. Okay, so that's how you do that sort of question. Quite tricky, actually. But yeah, we got there in the end. But that ruler did not help. Oh my god. Okay, so then we said we are given a graph, obviously the graph sine x that we have, and it's now reflected in the x-axis. Okay, so when it's reflected in the x, I'm going to get rid of this bit on the graph now that I've marked on it, just to make it clear what I'm going to do now. Reflected in the x-axis. Well, that's going to everything. So it's going to be reflected on this line here, obviously the x-axis. So that means it's going to be mirrored. So, for example, this point here is going to move up here. So -1 goes to 1. That will stay the same on the line. So this point here, this will move down to -1, and that'll be 0. So if you wanted to draw it, you don't have to, but it looks something like this. Okay, so you can see it's a reflection. But actually, what is happening here? Well, when you're reflecting the x-axis, think about what's happening. The x values do not change, but the y values are being flipped to the other side, aren't they? -1 turns to 1, and 1 turns to -1, and 0 stays the same, because obviously it's 0. What's happening here is the x values don't change, but a y value, our y values are flipping sign, they're becoming the negative to a positive, and so on. So actually, a y is becoming negative or positive, right? So it's flipping sign, as I said. So if we, in terms of functions, if if the x coordinates aren't changing, it's still f of x, right? Say if f of x is sine x here. Our x coordinate isn't changing here by the reflection, so the x so it still remains x inside. But our y values are they're essentially times it by -1, aren't they? We're flipping the sign of the y coordinates. The y values are changing sign. We're times it by -1, aren't we? So negative to a positive and positive to a negative. If we times each y coordinate by -1, that's the same as times in this f of x by -1, lots of f of x. But actually, that's just that same as minus f of x, isn't it, really? And that's what's happening. So the y values are becoming negative y. So, for example, if we had -1 minus a -1, no, sorry, we start here, we have 1. Then -1, that's -1, right? It goes to -1. Likewise, down here, we have -1 for y. So then that will go to -1, which should be with 1. So it will turn positive. So the reflection, that's how you work it out. But reflection, you should know, just looks like this. But you can easily work it out by trying some coordinates reflecting in the x-axis and seeing what happens to those coordinates. And here you should notice the y values are turning negative. They're flipping sign, right? Or turning negative or positive depending. But they're flipping sign, which means you're times them by -1. Okay, so that is going to be minus f of x, but of course, f of x is sine x, so it's going to be minus sine x. And that is your equation, okay? Y equals minus sine x here. Okay, and I guess you could say as well, xy, the general xy coordinate turns to x and minus y. So that tells you y is being times by -1 and x remains the same. So you times this function by -1. Okay, so now we are given another graph and we are told to draw the graph f of x minus 2. So we need to apply transformation. Okay, so in general, with these transformation type questions, you need to remember if we do something, anything, first of all, anything inside the function only changes your x values, your x coordinate. Anything outside the function, like we just had minus f of x, that affects the y value. Okay, so like we did here, it turns the y value change sign if you times it by minus 1. If we had 3 lots of f of x, you're timesing the y coordinates by 3. Okay, but with the when it's in the x, so when it's in the when you're changing the x, so anything happening inside the function itself, you do the opposite to what you expect. So here, we'd say x minus 2, you'd think we minus 2 every x coordinate, so you move down by 2 units. But you do the opposite. So instead of minusing by 2, we are going to add by 2. So we're going to add each x coordinate by 2, add 2 to x's, which means if we add 2, it's going to move 2 to the right, isn't it? So it's going to move 2 units to the right. So that's what we're going to do. So let's pick some key points here. So this is the 1 point here on the edge. We're going to move that 2 units to the right, okay, if we apply this transformation. So that's going to go minus 4 to minus 2, and it's going to stay here. The y values will stay the same, so we're just simply shifting it 2 to the right. Here, minus 2 will go to 0, minus 1 will turn to 1, and then 2 will turn to 4. And so really, we just connect the lines like on this graph here. So we're going to look at that, and then that. Okay, and that is our transformed graph. Okay. So we just shifted it 2 to the right. So what you need to remember is everything in the if you're changing the x part, the x values right inside the function. So here we have the x minus 2. You do the opposite to what you expect. So instead of minusing 2, you add 2. If we had f of a half x, or no, let's say 2x, and make it a bit more simpler. If at f of 2x, you'd think you're timesing in the x coordinates by 2, doubling it, but instead, that would be halving or dividing by 2 the x coordinates, right? Um, f of 4x, likewise, you wouldn't times by 4, you'd divide by 4, so you'd have a quarter, okay? But with the y, when you're changing the y values, like I said, the y, if you change the y values, you change the outside the function. So likewise, if you have 2f of x, so x remains the same because you're not changing anything with the x part inside the function, but you're changing stuff outside the function. So 2 lots of f of x, right? What you do to the y value, you do expect. Okay, so it's the opposite. So x is the opposite to what you expect. The y is what you do expect. So you'd think that's 2 times y. But yeah, so you double the y coordinates. If we had f of x plus 4, you're saying you're adding 4 to the y value. So you're shifting up, you're going up by 4, right? And that's what you expect. Whereas in this case, x minus 2, you're not shifting left, you're shifting right because you're adding 2, not minusing 2. Hopefully that is clear. So it all boils down to, with the x's, you do the opposite, right? So you do what you don't expect. And then with y, however, if you're changing y, you do what you expect. So you do what you expect. And that is the 2 fundamental key principles behind transformation of function questions like this. Remember these 2 things, it's actually quite a doddle, okay? But yeah, hopefully that made sense. I'm going to move on now. Okay, we have question 19. So there are 4 questions left. I can't remember. Okay, this is a vectors one. Okay. So we are given OT is A and RT is B. So they're given that on the graph essentially. M is the point on OR, and they've given that here as well. So it's that OM to MI is 2 to 3. Express MT in terms of A and B. So the best sort of thing we're going to do first is actually to visually see where MT is, and it's going to be here, right? Now MT, we do not have a direct way yet. So the best way with these vector questions is to find 2 different paths to get to the point, right? So instead of m to t, we could go and say m to o, which is here, and then o to t. Okay, and that is one way from going from m to t. Now we can work this out, can't we? Mo, well, we know OR. Well, we don't know OR yet, but we'll leave that there then for now. MO and O to T is simply A. Now, MO we do not know, but we know MO lies on RO OR. Okay, so I think if we find OR, we can then find out this MO. Well, let's try and work that out. So OR, well, O to R, like again, you can go from O to T, which is O to T, and then T to R. Well, O to T is simply A, and then from T to R, well, going this way, oh God, for R to T, going this way, it's positive B, but we're going from T to R, we're going backwards. So you simply flip it. So it's going to be minus B, not plus B. And that is your O to R. Okay. So we know O to R, but so what about MO? Because MO is on OR. We know stuff about it. I should say by the MO, this way, because we know what OR is. It's this way, right? A minus B. We know, no, oh no, it's this way, sorry. That way. O to R is that way. So M to O, first of all, that's just the opposite of OM. Okay. I think that's the best way of looking at it. MO is the opposite way of OM, which should be that way. But we know what OM is, don't we? Now, OM is OM to MR is 2 to 3. But if we add these parts together, which is 5, O to M and then M to R, that's just O to R overall. So overall, these 5 parts have to add up to O to R, right? So that if OM is 2 out of the 5, that means OM is 2/5 of OR. Okay. And that is the key strategy when you have a ratio with vectors. You need to consider what the parts add up to, and that would be your vector, right? And that would be the vector overall, right? So 2 to 3, so 2 parts and then another 3 parts. But overall, that's O to R, which we've worked out. 5 parts in total is the whole vector OR. So 2 out of the fifths, or 2 parts, is OM. So then 2/5 of OR gives us OM. Okay, hopefully that makes sense. So minus 2/5, but we know what OR is, it's A minus B. And then obviously we add the A here, because we have that here. So then minus 2/5 A plus an A, that's a 3/5 of A. And then minus 2/5 times the minus B, that's plus 2/5 B. Minus times the minus is positive. And that is your vector, that's one, well, yeah, that's MT. You didn't have to find another way, actually. That was it. That is MT in terms of A and B. I was expecting the vector would be nice, actually. But yeah, that's really it. So you just got to find a different way of getting to your desired point. Okay, that's the whole idea of these vector questions. Well, we can't go from M to T directly, but try and find other ways of getting there. Okay, it would work out exactly the same way if instead you went from M to R and then R to T. It would work out exactly the same way. Okay, but yeah, that's that question for 4 marks. God, I remember there was another vector question I did last time. And it was 4 marks as well. It's absolutely awful. Like simultaneous equations, it was loads of working. Ugh, but then compared to this one, my God, I don't know. But yeah, that's it really. Hopefully it made sense. So the big thing to realise is you can say OM is simply 2/5 of OR. Once you work that out, the question should be fairly simple if you practice your vectors, okay? Hopefully it made sense, right? If you add the parts together, that's going from O to R, right? So same as saying O to R, for example. 2/5 is O to M, so that's 2, and then 3 parts. Overall, from O to R is 5 parts, okay? So hopefully that makes sense. But okay, I'm going to move on. Okay, we've got a circle theorem question. Okay. So ABC are 4 points on the circle. SBT the tangent. Okay, I'm already thinking of what circle theorems I can use here. ABD is 20. And we're given some information about two sizes. Find the size of FBA. So again, the first step before anything, with these questions, I'm always going to ask you to find an angle. So the best way is to label the angle that, as x, like the one you want to work out. SBA, that's SB to A, that's going to be this angle here, right? If I get rid of it, it's this little angle here, which is going to be x. Okay. Okay. So, um, immediately we are told it's there's a tangent, so that screams two different theorems, right? Either two things circles I'm thinking of is either radius and tangent meet at 90, or the alternate segment theorem. But actually, we're not given anything about a radius, so really the only thing I'm thinking of is alternate segment. But I'm going to leave that there then for now. Um, we'll use it when that use it, but we are given some other information first. Let's work with that first. So we're given this angle 20, but we're also given this angle side BAD, which is B to A to D, which is this angle here, to the side of angle BCD, which is this angle here, is 3 to 1. So BAD is 3 lots of B. So if I call this angle Y, this is going to be 3y, okay? So BCD is a third of angle BAD, okay? That's what we're told. We can convert the ratio as follows. BAD has to be 3 lots of BCD, which we've got here. So we call this angle Y. We got an angle for, we can work out that angle as well. Okay, so what can we do now? Well, actually, we can actually find y, because I also noticed we have a cyclic quadrilateral, and the cyclic quadrilateral ABCD, and you should know opposite angles in a cyclic quadrilateral add up to 180, because these two are opposite angles, right? They're facing each other, so that means 3y. Immediately from that, I can deduce that 3y add y has to be equal to 180. And that's because opposite angles, I should say, add up to 180. But we can solve this now. It's a linear equation, so that means 4y is 180. So y is 180 divided by 4. That's going to be 45, right? Let me check that. Uh, oh, no, okay, yes, 45 there. I did the wrong one. I was meant to say divide by 4, but yeah, it's 45. So that's one, so that's great. We know two angles. But I also said alternate segment. But actually, isn't yx, because the alternate segment goes like this. Let's simplify this a little bit. We have a circle here, a very rough circle. Obviously, we have our tangent here, which is what we've got. If we draw one line from a tangent to the other part of the circumference here, which is D here, uh, this angle that we have here, if we then draw another line to another point C, and then we meet it at the same point on the tangent, it's a bit rubbish that is. Okay. Oh God. Okay. This angle here. So if we have on the tangent meets a point on the circumference here, say B, this corresponds to say corresponds to B here. This point. What's going on? Why are you deleting that? God. This angle here, right? That forms between the tangent and one of the lines. And then if that line meets the circumference, then it goes to another point, and that line hits the same point on the tangent. Then the angle that's subtended or made between that line and this line here, that is the same as this. That's the alternate segment theorem, because what you're doing here is, again, to illustrate, when you're creating, when you're um that line, uh rubbish circle, rubbish line even. When you have a line here drawn from the radius, so here I have the radius here, and then it goes from B to D, that's a chord. So a chord, by the way, just means a line that crosses between two points on the circumference, right here and here. That's a chord. And then a chord, obviously, you've got two parts of the circle, here and here, two sides of it. You've got two different segments, okay? So the angle in this segment here, this segment, is going to be the same if we then draw another, if we get another line in the segment here, that angle produced is the same. That's the alternate segment theorem, because the fact the chord produced splits the circle into two different segments, right? So the angles in those two segments are equal. So then that means x then, or angle SPD, or SBA, that has to be also equal to 45 because of the alternate segment theorem. Because the tangent meets this line here, BD, so that's the segment here, and then this whole segment here. But then we draw another line that hits the circumference, and then that goes to the tangent. And that's the angle y. So this angle y is be equal to this angle x between the radius and that chord. No. And no, that's not x. Sorry, this x plus 20 has to be 45. My apologies. X plus 20 has to be 45 because it's this angle x and the 20. So the tangent and this chord BD, the angle is, oh my God, there we are. It's this whole angle here. Oh, it's a bit rubbish that is. Oh, yeah, when I write more stuff down, it becomes a lot slower, my laptop. It's so annoying. It might be because I'm recording as well. There's too much stuff going on for my laptop. Quite a rubbish one, but we have to work with what we've got. Uh, so it's this whole angle here. It's the 20 and this angle x combined. That is the angle between the radius, not the radius, the tangent, and this chord BD, this line chord BD. So x plus 20, 45, which is the y angle here, which is 45. So therefore, as a result, x is 45 minus 20, which is 25 degrees, which is angle SBA, right? because that's that X here, SBA. Okay, hopefully that's okay. That's circle theorems, right? So again, think with what you know. Usually, like I said, with circle theorems, there's usually a circle theorem that screams at you at the start. Why don't I want to? What's going on, man? Go away. Uh, oh my god. So at first, the fact they're giving us a tangent is a dead giveaway. There's a tangent and there's no radius, so that screams alternate segment theorem. Um, but then I noticed there's a cyclic quadrilateral as well, so that screams the opposite angle theorem as well. Yeah, so that's how we get to that. Quite a nice circle theorem question that is. But I had to pay attention to that bit at the end. It's the whole angle x plus 20 because that's the angle produce the tangent BD and the tangent. Okay. Okay. Talking about tangents, we've got another circle theorem, quite circle question. And this one's quite common as well. On vast majority of past papers, on one of the calculator ones, or one of the papers, I guess, in general, there's a circle question like this. Okay, to do with lines and stuff like that and gradients. Let's read through it. So this is the second last question. So if you made it here, good job. So we're given a circle with equation x squared plus y squared is 25. The point P with coordinates minus 3, 4 lies on the circle. So on the circumference. He says the tangent to the circle crosses the x-axis at that point. Okay. So let's go through it step by step. So circle with these type of questions, it's a very, very, very good idea to sketch the graph, right? So sketch the circle. So you should remember x squared plus y squared in the form of r squared. R is the radius, okay? Squared. So 25, 5 squared is 25. So 5 is the radius here. And it's centered at the origin. So we start from 0, 0, and we go 5. So 5 here, 5 here, 5 here, or minus 5, and then minus 5 here. So then a circle's going to look like that, okay? That's our circle. Now, a point with minus 3 and 4, that's going to be about here, isn't it? This P, because that's going to be minus 4 and 3. Minus 3. No, sorry, P. Minus 3 and 4, that's going to be here, sorry. Now I've got rid of the circle, God's sake. A very rubbish circle this time. No, but minus 3 and 4, no, sorry, it's going to be here, isn't it, roughly? That's going to be P. Because 4 is going to be about there, isn't it? So that's minus 3, 4. That's P. Okay. So that lies on the circle. Cool. So the tangent to the circle at P crosses. So the tangent is going to look like that, right? The tangent to the circle at P is going to be there. So that's our tangent. So we need to find the equation of the tangent, right? So remember, the general form of a line is y equals mx plus c, where m's the gradient and c is the y-intercept. You should always start off with that. That will help you a lot better. Once you draw the graph and you recognise this general form, the question becomes a lot better. Like it becomes a lot more clearer what you need to do. So what we need is the gradient and the gradient and the y-intercept. Okay. Well, we know 1 point on the line, but that's not going to help because we need 2 bits of information. We only know 1 point, so that's not going to help us yet. Okay, but you should know that actually we know the center and we know a point in circumference. So actually, between the center and P, that's going to be the radius, no? So actually, if we work out an equation for the tangent, so this is our tangent, right? If we work out the equation of the radius, well, they're perpendicular, aren't they? Because of the circle theorem, that radius and tangent are perpendicular, which means they meet at 90 degrees, right? So I think let's do it. So again, so our equation of a radius, well, we know 2 points, don't we, on the radius? So 0, 0, which is our centre, and again, and then this radius from 0, O, goes to P. So minus 3, 4. These 2 points lie on the radius. So therefore, the gradient of the radius, that's going to be change in y over change in x, right? That's just your normal gradient formula. So the change in y, that's going to be 4 minus 0. So 4 here minus the 0 here. And then minus 3 minus 0. That's going to be minus 4 over 3. Okay. Well, that's the grade of the radius. Oh, God, what's it doing now? That's the grade of the radius. Cool. But then the radius and the tangent are perpendicular. So that means you should know between perpendicular lines, the gradient of the other is the negative reciprocal. So that means the gradient of the tangent is going to be 3 over 4. So you make the reciprocal, which is 4 over, flip the fraction, which is 3 over 4. Then you do the minus. So minus of minus 3 over 4 is positive. So that's the grade of the tangent. That's m, isn't it? So that means y is 3 over 4x plus c. That is your m, your grade of the tangent line. So then to find c, well, we can just then, we know p lies on the tangent. So we're going to sub minus 3, 4 into line, aren't we? Because we know this point minus 3, 4p lies on the tangent, right? Because it's tangent to the circle at that point. So that means then 4 is going to be 3 over 4 of minus 3 plus c. So that means 4 is minus 9 over 4 plus c. So c is going to be 4 add 9 over 4. And you could put that in the calculator. 4 add 9 over 4. And that gets you 25 over 4. But then now we found the C, the y-intercept. So that means I'm gonna write this up here now. So that means actually I'm gonna create more space actually. I thought, well, hopefully it doesn't bug out like I did last time. Okay, there we are. So that's our C. So therefore our complete equation now is y. That's going to be 3 over 4x plus 25 over 4. Okay, so now we found our complete equation for the gradient. What's it asking us to find? So the tangent, sorry. The tangent crosses the x-axis at this point minus 8, 0. Is he correct? Well, we need to substitute that point in and see if it is indeed true. So we need to see minus 8, 0. So you then could say 0 is 3 over 4 of minus 8 plus 25 over 4. So 0 equals, then put all that into the calculator and see what you get. If you get 0, then that should be right. But if not, then something's gone wrong. And he might be wrong. Anyway, so 3 over 4. Let's type that in. 3 over 4 times minus 8 plus 25 over 4. You get a quarter. So actually, it's saying 0 is equal to a quarter. 0, 4. Well, this is not true, is it? This is not true. That cannot happen. 0 is not a quarter, clearly. So that's not true. So Alex must be incorrect. So it doesn't pass through minus 8, 0 because it doesn't satisfy this equation. So it cannot. This line cannot. This point cannot be on the line. Okay? So Alex must be correct. Okay, cool. So that's hopefully it made sense. So with these sort of questions, don't freak out. But drawing a graph of the circle massively helps. So the key idea, the central idea of these sort of circle questions is you consider the radius, and the radius you can form an equation because it's between 0, 0 and the point. So you can form an equation with the radius, and that will be perpendicular to the tangent. That will mean you can get the gradient of the tangent, and then you can find the equation of the tangent, right? Because you know the gradient. Okay, so that's the whole idea of these sort of questions. You can always consider the radius, right? And then that'll get you where you want to. Okay, I'm just going to go to the toilet while you have. I guess you can look at this. It's the final question. It's a very monstrous question, but I'll leave you go there for. You can look at it for a minute and see what you do. Okay, we are back. Okay, so hopefully you should recognise this is the bounds question. Um, I'm going to need more space for this for sure. Okay, let's have a read. So, it said Jackson is trying to find the density of a block of wood. The block of wood is in the shape of a cuboid. He measures the length, the width, and the height. He measures the mass as 100 as this number, and by considering bounds, work out the density of the wood. So it's a bounds question because it's given all these units, all these numbers correct to the nearest millimetre, to the nearest 5 grams. All of these numbers are rounded, so that's going to create a bound. Okay, so it's a bounds question. But it's a lot more involved than the typical bounds question. Okay, so we're going to need to work some stuff out first. So first, mainly, it's asking us about the density. So you should know the density. You should know this formula, right? Like with speed, distance, time, it's mass, density, and volume, right? But this triangle here. So we want the density, so we're going to cover that up. So that's going to be mass over volume, right? So the density is mass over volume. Okay, cool. But we know the mass, it's given as this, although it's rounded, but we're given the mass, but we're not given the volume. But we are given the three measurements of the shape, though, the length, the width, and the height. Can we not work out the volume from that? I think we can, because it's a cuboid. Oh, for God's sake. So the volume, in general, would be the length times the width times the height. Okay, but we can't work this out directly because they're all rounded, so we're going to need to consider bounds before we plug any numbers in. Um, So it says, considering bounds, work out the density of the wood. So what we're going to need to do is actually work out the lower and the upper bounds of all these numbers. So that's where it gets quite involved. So we need the upper and lower bound for the density, which means we're going to need the upper and the lower bound for both the mass and the volume. And therefore, we're going to need the upper and the lower bounds for each of these units as well, each of these measurements. Okay. So the mass is easy, right? So the mass of the mass is, well, 1970 is 5 grams. So we need to do the upper and lower bound. So if we round just to the nearest 5 grams, so that's going to be 1965, 1970, 1975. So it rounds to these numbers, right? Every 5 grams. So what number is going to be the highest that are round down to 1970? Well, it's going to be in the middle here between 1975. So it's going to be 1972.5. So we're going to add 2.5. So we're kind of doing 5 divided by 2 here to give the bound. And that makes sense, right? 1972.5 to the nearest 5 that are round up. But the number before that, 1972.4999, that were round down to 1970. Okay, hopefully that is clear. Because this is closer to 1970 than 1975, right? This 4.9. So it will round down to not 1970. That's the whole idea, right? So say if we had 1970 and 1975, right in the middle is 1972.5, right? Anything below that is going to round down. So that is our upper bound. Likewise, our lower bound is going to be subtracting 2.5, the midpoint, right? The middle. So that's going to be 1967.5. That'll be your lower bound. Okay. Okay, can this wrap? Okay, I want to get rid of this now. That's the sort of idea, right? Of these bounds, right? You need to think the highest number that are round down and the lowest number that are round up. And hopefully that sort of diagram helps, right? If you consider like on the number line between the two numbers, that in the middle it have to round out and so on, like we just did. So those are bounds for maths, right? Now that's maths, but now we need to deal with volume. But the volume is given by this product here. We don't have an actual number by itself. We need to times these three. But we need the lower and the upper bound for the volume. Well, if you want to maximize the volume, so the max of let's say V max. For God's sake, it's so slow now. And the computer wants to give up. So V max or vol of max, the max volume, so the upper bound, or pretty much. Actually, I have to say volume upper bound. Actually, vol UB for upper bound. Well, if we are times in three numbers to get the maximum possible number, you're going to want the maximum of these three numbers individually, aren't you? So you're going to want to times by the upper bound of the length, the width, and the height to get the upper bound for the volume, right? So you're increasing the volume as much as you can. So if you times in by bigger numbers, you're going to get a bigger number, right? So that's the whole idea. So it's going to be length of the upper bound times the width of the upper bound times by the height of the upper bound. But we are given these three bounds individually, right? So the length, or L, that's 13.2 to nearest millimeter. So the millimeter, because this is in centimeters, the millimeter is the decimal point. Okay, so the nearest decimal place. Because obviously 1 millimeter or 10 millimeters is 1 centimeter. So it's a decimal point. Okay. So if we round to the nearest decimal point, pretty much of 13.2, the upper bound is going to be 13.25. Okay. Because anything, God, 13.25. There we are. Because anything below that is going to be round down to 13.2 to the nearest decimal place. So we're going to add 0.05, subtract 0.05, that's going to be 13.15, and that will round up to 13.2. That's your length. Your width is 16.0, so 16. Again, that's to the nearest millimetre, so to the nearest decimal place, it's going to be 16.05, isn't it? If you add 0.05, that's your upper bound. If you subtract 0.05, you're going to get 15.95. And your height is 21.7. So I'm reading it here, by the way. Again, to the nearest decimal place, oh, for God's sake, that's going to round up to 21.75. So you add 0.05, subtract 0.05, and then that's going to be 21.65. Okay, that's your upper and lower bound for your height. So now we've worked out the upper and the lower bounds. Well, then the upper bound of volume is going to be the upper bound of all three of these. So it's going to be 13.25 times by 16.05 times by 21.75. Okay. Put that into the calculator and you get let's move it here. That's going to be this number here. 46. What was it? 4625. And our decimal points are going to be important here. We are going to have to write this out. 4625.409. And that is your upper bound for your volume. So volume upper bound. Okay, so that's the upper bound, but we also need the lower bound. So I'm going to write that down here. Your volume for your lower bound, well, again, if you times it three numbers to get the smallest number, you're going to have to make the numbers small. So the smallest possible number times smaller numbers, you get a smaller number, right? So again, think of, say, for example, 3 times 4, 3 times 4 times 5, and then 5 times 6 times 7. Which product's going to be bigger? This one, right? So to make a smaller multiplication, you're going to have to make the numbers as small as possible. Okay. So your lower bound is going to take the lower bound of all of these three numbers here: your length, your width, and the height. So 13.15. Oh God, what's going on here? There we are. Oh, I don't know. 13.15. That's your length or lower bound length. Lower bound width is 15.95. And then your lower bound height is 21.65. So put that into the calculator and you get you get this number here, 4540. Ah, 5. God, it's messy. 4540. 0.925. Again, you just have to write them all out. Because we're dealing with bounds, the accuracy does matter with the decimals here. 925.125. Okay. And obviously that'd be ongoing. So, yeah, so now that's our lower and upper bound for the volume. We know our mass upper and lower bound. So now our density, we can work out the upper and the lower bound, can't we? So therefore, so the density of the lower, let's do the upper bound first, the UB. Wow, it's this division here, mass over volume. If we want the density, this number to be as big as possible, we're going to want to divide them. We want to make the top number and the mass as big as possible. So that's going to be the mass of the upper bound of the mass. And you're going to want to make the volume as small as possible. Because if you divide a bigger number by a smaller number, the fraction is bigger. Think of it like this. Again, pick an example. 6 divided by 3 is bigger than. Now let's pick a nicer number to work with. 8 over 2 is bigger than 6 over 3, right? 6 over 3 is 2, 8 over 2 is 4. So making the numerator, the top number, the numerator bigger and the denominator smaller gives gives a higher number than making the denominator smaller, the top number, the numerator smaller and the denominator bigger. Okay. So you picking a bigger number, you dividing it by a smaller number. That will maximize or increase the number, right? So that's really what we're going. That's what we're going here. So that's why we pick the bigger number for the mass and the smaller number for the volume. But we know these bounds, don't we? So let's substitute it in. So the upper bound for the mass is 1972.5 divided by the lower bound, which was this 4540.925, so on. And then put that into the calculator. Well, we already have the 45 from earlier. So that's going to then be 1972.5 divided by our answer. Oh God, what's happened now? Oh, okay, there we are. Divide by our answer, and you get this number here, 0.43 438 285.06. Okay, so that's your upper bound. Okay, cool. Now we need to do the lower bound, right? So the density of the lower bound. Again, now we want to make the division the number as small as possible. So we're going to do a smaller numerator. So the mass is at lower bound. Because you're now going to divide a smaller number by a bigger one. So we're going to need to take the upper bound for the volume, okay? To give as small number as possible. Okay. I guess the way to think of it as well, if you're a bit struggling, this is the same as saying 1 over volume times by the mass. Well, think about it. 1 over 5, 1 over 6, 1 over 7. As you're increasing the denominator, hopefully you can see that that will be a smaller number. Okay, that will go to 0, right, as we divide by high numbers. But then we times it by mass. So if we times by a bigger number, you get a bigger fraction. So that's why if you want the higher number, you get the higher numerator, because you're essentially timesing by the numerator. 'Cause it's the same as this. So times it by a bigger number gets a bigger fraction, and if we divide by a bigger number, the fraction becomes smaller. So to get the bigger fraction, you want this to be as small as possible. This fraction, so the volume has to be as small as possible, and the mass has to be times it by a bigger number, so the mass has to be bigger. And it's the flip side for the lower bound. Okay, I don't know. I'm just trying to give multiple ways of explaining it. But I don't know. There's many ways. Whatever makes you wrap your head around it, you know. But anyway, so let's get on with it. The lower bound. So the mass of the lower bound we know is 1967.5, which is up here. And then your upper bound for the volume is, we worked it out here, wasn't it? Wasn't it? It was 4625 point 409. I won't let me scroll down now. 409. Oh, for God's sake. 409 375. And so we need to put that into the calculator. And so that will be 1975. 1967.5, sorry. 1967.5 divided by 4625.409375. I hope I brought the numbers down right. I probably did make a mistake somewhere. Anyway, that goes to 0.4 to, what was it? 0.4253677 uh 546. So we've got a lower and upper bounds around it now, right? So that's the question really. So it said at the end, work out the density of the wood. So we need the actual answer. We need a single numerical answer for the density, and we need to consider bounds. So what that means is when you have something like that, you need to round the density such that the lower bound equals the upper bound. Well, 0.4, so the first digit, yep, they both are the same, 0.4, 0.43 and 0.42. Well, 3 is different, so that's different, but if you rounded it to two decimal places, the 4 is less than 5, so it'd be 0.43, and then 0.42, again, that's 5, so actually it will round up to 0.43. So to two decimal places, the density is going to be 0.43, and it's equal to that when both the upper and the lower bounds agree. So when they both to the same decimal place, they both round to the same number. When that happens, so the density is this because to 2dp, the upper bound and lower bound round to the same answer, right? Which is 0.43. So in a sense, if the lower bound then equals the upper bound, well, that has to be the density, right? That has to be the number 0.43. That has to be. There's no wiggle room there. So to two decimal places, it's 0.43, and actually, I guess with units, it's going to be grams per centimeters cubed, isn't it? Let's check the units. I don't think it matters, but yeah. Yeah, so the units would be grams per centimeters cubed. That's because the mass is in grams and the volume's in centimeters cubed. So it'd be grams over centimeters cubed. Okay. And that's it. That's the bounds. That's really it's actually not a bad question. It's just a lot you need to work with, right? It's not a typical bounds question. They give you a formula and you just got to plug the numbers in. You got to work some stuff out yourself, right? There's a lot of bounds you need to work out. But yeah, and that was the final question in 2018 paper 2. So this was a final question. This was a grade 9 question. Oh yeah, it says it there in grams per centimeters cubed. There we are. It's actually mass. So density is 0.43. Okay, so that's that there. Oh man. Okay, so that's that paper done. What I'm going to do now is I'm going to check my answer and scroll through back the paper and check my answers. But in the meantime, you can check the work, and if you want to, let me zoom out actually, if it lets me. There we are. At the under view. But you can check the questions one final time as well. You can look at my working, do whatever you want with the working out. Okay. So I hope check my answers should be okay, but you never know. It's always a mistake I make somewhere. Some silly mistake. Okay. Yeah, 0.43 to do decimal places. That's correct. Nice. Uh, um, yep, he was wrong. Yep, same sort of answer. Okay. Also, by the way, you can use this time to ask questions. By the way, once was obviously on Twitch, obviously on playthrough. Where you, if you're on YouTube, don't feel free to ask a question if you I'll try and answer it. But use this time to ask anything as well if you want. I'm trying my best to answer it if I can. While I look for my answers. Yeah, we've got 25. Cool. Uh, 3 of the fifth A plus 2 of the fifth B. Yeah, cool. 56, 144, 396, 504 minus sine x. Cool. Yes, okay, that's right as well. Cool. Oh God. Okay. Minus 11x plus 2. Great. Yeah. Cool. Uh, 7.63. Yeah. Cool. Uh, yep. That's right. Let me check the chat. Okay, I think we're good. Go. 2n squared plus n plus 1. Great. Yeah. That should be fine. I'll double check it though. Yeah, that's cool. I'm fairly confident that's right. I don't know. If I'm wrong, pull me up in the comments, but that should be okay. 580, 6354.67. Cool, lovely. 18 to 15. Yeah, cool. 10 to the 60. 10, 12 to the 100. Yeah, cool. 65 days. Yep, cool. Okay, that's right. I believe. 57.1. Oh, okay, that rounds up, but yeah, it doesn't really matter. The time must be the same. Yeah, so the time between the two journeys is the same. I might explain this in the comments a bit better if I can work out a better way of explaining this. I don't know. I think a bit iffy there, but I don't know. It's only a mark, I guess. But yeah, it's the whole idea. The average, if you divide by two, then it has to be equally split apart, essentially. So the times have to be the same for both of them. Okay. 17.5 hours. Cool. Uh, 2/10. Yep, cool. That's fine. There is a one there. I don't know what happened there though. Probably accidentally rubbed it out. So I don't know. Okay. Yeah, that's fine. So, yeah, 7.5. Cool. Okay, this one. Okay, let's check that one. 2023 paper 2. 1.67. Yeah, 1.6. Okay, cool. So that's all right. Okay. Oh my God, it's like the first time ever I've not made a silly, even a silly mistake. Completely flawless. Live. Wow. Okay. Buzzing with that one. Usually I make a silly mistake. I write down the wrong number or something like that. Just copy the, I don't know. Or handwriting a mistake a negative or positive or something like that. I don't know. But we got that's all right. Cool. So that time as well, you could use that to, after chat or obviously look through the questions one last time. Um, but yeah, there are no questions, at least for me at the moment. So I am going to leave that there then, not to drag this on any longer. But I will be on tomorrow as well, doing another stream. I'll be doing the same thing again, compile similar sort of questions from past papers or whatnot, and we'll do the same sort of thing again. But yeah, that's it for now.